Yeah, good evening, good morning, everybody. Can you please see me as well as can you listen me? Please raise your hand. Yes, everybody, good morning. This is Krishna Verma, B.S. Krishna Verma from ACE Engineering Academy, faculty since 2009. Okay, so because of all the combinations that happened, and even I was also busy completing the batches. Now, your batch I am starting today. Now, this is exclusive triply, right? Can you raise your hand again? Yes. So, see, sir, what is the idea is today I'm taking 7 to 10, but what is my idea is I forgot about breakfast. Like, if you are okay, because you are all completed students or whatever it is, initially 1 week I will go 3 hours only, sir, and slowly I will increase to 5 hours. More than that, it's not good in online coaching. I am not comfortable teaching 6 hours, 8 hours. Please understand that. Okay, and also I am teaching offline batch also, sir. So that is another reason I will be very busy. But as we go, we will improve the timings and we will conclude. So today, yeah, I told 7 to 10, but I will take break at 8:40. Now it is 7:10, so 8:40 to 9:10 I will take break, and 9:10 to 10:30. Is it okay for you? If I extend up to 10:30, 10:40, is it okay for you? Please raise your hand again, everybody. Okay, but 3 hours pakka I want to teach, sir. See, what is my intention is not so specific, but 3 hours content. My idea is to cover 3 hours content. Okay. Okay, this class is for BTech passed out or for all students, including college goers. I really don't know about it, sir, but I really don't know that you should say because schedule managers give us the batch and we cannot identify which students are there here, which I don't know. I don't know, please. And okay, this is for college goers too. Okay. Some students say today we will close at 10, tomorrow onwards we will go up to 10:30 and break only break 15 minutes is not possible, Bharat. Not possible. See, 15 minutes in my house also, though I'm staying at my home, 15 minutes I cannot have breakfast because madam has to cook, etc. Whatever it is, okay. So we will decide that. No, 6 to 10 again is not worth because so many students. I am ready to get up at 5 o'clock, but what about others? Okay, we will decide all these things. Please don't give me suggestion. Don't give me suggestion. If I ask anything, you say yes or no. Okay, but don't give me suggestion, please. Because everyone has their own personal requirement, and if I go that way, all 300 students have to satisfy, which is not possible. Okay, so we will start the session. See, my video sometimes it automatically turns off based on the internet connection, and sometimes I purposefully turn off because of this video. Sometimes the speed will affect internet at my side. Audio will be there running always when I am speaking, but video some now and then I will be turning off. Okay, so that you please understand, and we will start the session now. So this is network analysis. Yes, that is what I say, or electrical circuit analysis we call. Okay. It is a big subject for electrical people. Okay, it is a very big subject for electrical people, as it is huge in terms of marks and content. We will do very carefully. Okay, we'll complete all the things. Okay, very carefully. Okay, I'm starting now session. Okay. Now, what are the average marks? First of all, let us talk exam point of view. Okay, the average marks. Okay, in my subject, if it is GATE, average is 10 marks, but range is 8 marks to 12 marks, and even sometimes 17 marks came, but general range. So average is 10 marks, sir. Average is 10 marks. Okay, that means out of 100 marks in GATE, 10 marks, 10% is my paper only. Please understand. Okay, my subject, electrical circuit analysis. And when it comes to ESC or most of the UPSC exams, again it is 10%. 10%. Please understand. It is again 10%. Okay, like in prelims, you know, 150 bits are there, 180 minutes, and it is 300 marks. So 10% is 30 marks. Overall 30 marks you will get only from network theory or electrical circuit analysis. And I want to even mention that in exams, state board related exams like state government exams like GENCO, TRANSCO, okay, DISCOMs, okay, distributed corporation, okay, staff selection commission, SSC, so many other exams also it is 10%. So in electrical engineering itself, this subject is highly dominant. Yes, and it is 10 marks in GATE. UPSC prelims I'm talking right now. Okay, I'm talking with respect to prelims. Mains, it is 84 marks. Okay, here I will mention that ESC mains in paper 1, it is 84 marks out of 300. 84 marks out of 300 is only network theory or electrical circuit analysis. Okay. So first, in terms of marks, yes, please understand. My subject in GATE is around 10 marks, minimum 8, maximum 12. In 2 times, it went even up to 17 marks, but generally, average is 10 marks. And in all other exams like UPSC, civil services, GENCO, TRANSCO, IES, 10% of the marks. Okay, 10% of the marks, please understand. Okay, in IES mains, of course, in mains, paper 1, 300 marks conventional. In that, 84 marks is network theory. Sometimes it went up to 92 also, but 84 is the average. Okay, so this is a very, very dominating subject. Please understand this. Then, okay, how to get full marks in network theory or electrical circuits. Okay, electrical circuits. Okay, so I'm writing something here. That is how to get full marks in electrical circuits. Okay. Step 1. First, notes. Notes perfect. Okay, now, sir, everybody please understand. You be perfect with my notes. All models, revise again and again. Revise 3 times at least. 3 times at least. Okay, because it is a highly practical subject or practice subject. So what I want to say is everyone should revise this. Just one time reading and one time listening is not sufficient. All the problems you do now and then whenever you are free, because it is a highly numerical paper and numerical subject. So please understand that. So I want everyone to really listen and also practice multiple times. Okay, that is the first suggestion that I want everyone to do multiple times. At least 3 times you have to revise and do again if necessary also, sir. Yes, do again if necessary also. Then step 2. Step 2, first to do, after completing my notes, first to do ESC objective. ESC objective solved papers of both EEE and ECE. Of course, in IES it is called electronics and telecommunication, E and T. Okay, ECE in IES is called electronics and telecommunication. Okay, don't worry. So what I suggest is, my subject is common for EEE and ECE, na sir. You take both the objective solved papers and do it, please. Okay, na, please do it. I want you to do it. Objective solved papers, both EEE and ENT, electronics and telecommunication, at any cost. Though you are a GATE student or GENCO student, first do IES objectives, sir, because IES objectives will give a lot of basics, formula based bits. Okay, substitution bits, match the following, fill in the blanks. So a lot of theory and fundamentals you will get, and IES bits are easy compared to GATE. So first you should need that mathematical basics and fundamentals where calculator is not allowed. You know that all IES bits where calculator is not allowed, so that speed will come, accuracy will come. Then step 3 is, okay, then do GATE bits. Okay, GATE solved papers of EEE, ECE, and even instrumentation. See, my subject is common for all the 3 branches, and every time papers are completely different. So sometimes EC bits are very good, sometimes EEE, sometimes instrumentation. So all the branches, my subject, solved papers you solve. That is the best guide, sir. There is no other book which will give so many unique problems anywhere in the world. There is no other book in the world which will give so many unique problems. So I expect you should do that. GATE papers you do next. Okay. Then step 4, write lot of practice exams. Please write lot of practice exams. From December ending or December 15th onwards, everybody, please understand, write lot of practice exams, online, offline, mock test, grand test, lot of exams we put in ACE Academy. Please do that. Please do that, sir. Take these exams serious, because time management is the biggest thing. Okay. Then step 5 is only for IES students, only for ESC mains. Okay, one simple textbook, solved examples plus previous ESC conventional solved papers. Okay, everybody listen now. How to get full marks in my subject? Everybody should listen. See how to get full marks in my subject. See, though I give notes, in my notes all models I will cover at one place, making it very simple and compact for you. But still, first step is to solve for IES objective, both EEE and electronics and telecommunication branch. Then go to GATE papers. Directly don't go for GATE papers, sir. But first IES you do, then go to GATE papers. Then lot of practice problems. Okay, lot of practice exams, sir. From December onwards, you please do that. And IES conventional, this 5th step is only for IES conventional. Okay, I want to mention this step 5 is only for conventional, that too after clearing mains. That is one simple textbook, solved examples, and previous ESC conventional papers you solve. Okay, so with that you will get full marks in my subject. Later, if time permits, I will write here, if time permits. Okay, then solve GENCO papers. Okay, like your state board GENCO, TRANSCO papers. Okay, JTO papers, JTO solved papers. Okay, JTO solved papers. Okay, all these books, and UPSC, civil services, even their electrical engineering is there, solved papers. So these all books available in ACE Academy, in ACE Engineering Academy. Okay, na? So you can go to our ACE website, publication section. There you can prescribe whatever book, and they will send you through courier. This you have to buy, sir. See, once you are preparing these 5 steps or 4 steps, sir, later suppose GENCO notification come, na, sir. After preparing these 4 steps, then only GENCO papers you do. So many papers we have solved, sir, at one place. GENCO, TRANSCO papers, JTO papers you do. That is my suggestion. Okay. Now I'm never referring any textbook, but still I will write here the best books to refer, best text books to refer. Okay, best textbooks to refer. 1, fundamentals of electric circuits. by author is Alexander and Sadiku. Alexander and Sadiku. Okay, this is my number one choice. Okay, Fundamentals of Electric Circuits by Alexander and Sadiku. Then second is Engineering Circuit Analysis. Engineering, okay, circuit or network analysis by Haight and Kemmerly. Haight and Kemmerly. These two together is an ultimate combination. Two together is a combination. First author is an electrical author who wrote power level. Second author is an EC author who wrote signal level. Both together is an ultra combination, sir, ultimate. But sir, I'm never asking you to read textbook, sir. There is no time. That is why you see in my steps which I wrote. Did I mention textbook anywhere? No, sir. No need. If you want full marks also, do what I say. First read our notes perfectly, revise 3 to 4 times, every point you have to remember, every formula you have to remember. Then do IAS objective, both electrical and EC papers, then gate solved papers of electrical, EC and instrumentation, my subject which is common. Then do a lot of practice exams. And then if time permits only, yes, that specific exam papers, like suppose you are writing JTO, ISRO, yes, even ISRO I will write, sir. ISRO papers are there. So many papers are there, sir. ISRO papers are there. So these are all such special books you have to subscribe and buy from ACE Academy, sir. You will not get these papers anywhere in India, I am telling you. These are a collection of question papers at one place, and all these books are available in ACE Academy. Okay, now all these books are available in ACE Academy. You can buy them through our website. Okay, now so then if you want any specific textbook, I prefer these are the best books as a guidance only. Okay, these two are only for the guidance, please. I'm never entertaining you to buy it. Never. Please don't do that. There is no time. Even if you want top rank, don't do that. My subject is fundamental and basics. But these two are my reference books. So if you say, sir, which are the best books you follow, I follow these books. One is Fundamentals of Circuits by Alexander and Sadiku, and one is Engineering Circuit Analysis by Haight and Kemmerly. Okay. And before I start, everybody, see, doubts will be cleared only at the last. Okay. Yes, if there is any mistake, you intimate me. But generally, doubts will be only after the session. Okay. Today I will close by 10. Yes, today I will close by 10. But generally doubts I will take only after the session. But tomorrow onwards, I'm again announcing tomorrow onwards timing will be 7 to 8:30 first session, 8:30 to 9 break, and 9 to 10:30. And after 10:30, I will take doubts. Okay, that is a plan, sir. Everybody please understand. Today I will close by 10 because I did not intimate you. Yes, I will close by 10. Tomorrow onwards, please listen, 7 to 8:30 first session. Then we will take a break of half an hour. Then from 9 to 10:30 second session. Okay. And after 10:30, you can ask doubts. And ask doubts which is relevant to my subject and which is relevant to what I did teach you that day. Okay. But you have to wait and have patience, because by the time I complete, you will never get doubts. So initially, don't be in a hurry to ask everything. Slowly, gradually, you see when I complete everything, I am 100% guarantee that you will never get doubts in my subject. Okay. Later, I will give my WhatsApp number, and also I will share my personal notes, etc. with you, apart from daily notes. Okay, na? Plus textbooks, etc. with solution manuals also I will share. So all this plan is there. I will implement it gradually. So you just listen to what I say and listen to my instructions. Okay. So doubts you will not interrupt in between, because there's such a big batch, sir. Here already 400 students are coming. So I need to be very careful. Okay. So individual doubts I cannot entertain, but after the session is over, you can ask me doubts. Okay. Is that okay? Everybody raise your hand. Okay, so please have this discipline and understand the problem from my side also. Okay, and I turned off video because of internet speed and problem. Sometimes voice get breaks. That is the reason. Sometimes I will turn on my video also. Okay, don't worry. So please cooperate, sir. I know it is already October 16th and it was delayed my subject because of many reasons. Okay, some things I cannot share with you, but disaster happened. I got COVID. My father died. My father died in the month of April, not because of COVID, but due to heart attack. And 3-4 months I was not there I was not in a mood to teach, and that also delayed. Okay, all these are the problems that happened, sir. Please understand. Okay, my father died recently on April 21st this year. Okay, due to heart attack, and I got COVID later, and I was also hospitalized for almost 7 days, 8 days. Okay, so all these are the problems I faced in my life personally, and due to which also this professional career got affected. But slowly I'm recovering and I'm slowly teaching now. And that is the reason I requested some of the students to have patience also. I remember some students were calling me, sir, you did not start networks, etc. So I told them what is the reason. I hope you understand that. Chalo, everybody, we will start the session now. So now my subject is divided into 3 parts, sir. Okay, everybody listen. My subject is divided into 3 parts. See, part 1 is about ideal DC circuit analysis. DC circuit analysis. Okay, na? Part 1 around 33% to 35%. Okay, I will say 35% and more is only DC. And sometimes it can go up to 40%. That means in exam also, out of 10 bits, 4 bits come from DC only. Now, in ideal DC, you know the signal. Ideal DC look like this. Okay, now suppose it is a voltage versus time. Ideal DC voltage look like this. Suppose some A volts. Okay, now A volts look like this. Now, when I give ideal DC signal, you know here dV by dt is 0 and also di by dt is 0. Okay, for ideal DC signals, dV by dt is 0 and di by dt is 0. And when dV by dt and di by dt is 0, only resistor will perform. Resistor is performing, which is a homogeneous and proportional component. Proportional component in behavior. Component. That means it will obey Ohm's law. Like DC voltage will give DC current, but pure inductor acts like short circuit. Okay, and pure capacitor acts like open circuit, because in inductor V is L di by dt, na sir? Because di by dt is 0 for DC. Okay, because di by dt is 0 for DC. Okay, inductor acts like short circuit, and in capacitor, because dV by dt is 0, I is also 0, it acts like open circuit. I will tell you, don't worry, these are all basics. Everything I will tell you with proof. Okay, not that I'm in a hurry. This is introduction class. So my subject first part is DC circuit analysis. It is covering 35 to 40%. When I give ideal DC signal to my circuits, dV by dt is 0 and di by dt is 0. So resistor only behaves. Okay, so DC circuit analysis is all about resistor circuits only. Because inductor and capacitor, they don't work. Ideally, inductor acts as short circuit and capacitor acts as open circuit in steady state. In steady state, that is important. In steady state, settled state. That is why only resistive networks we do. But where is ideal DC? Ideal DC we get from where? See, ideal DC we get from newly purchased cells or batteries. Okay, cells or battery and voltage regulators. Okay, precision voltage regulators. Precision voltage regulators. Regulator ICs. Not everywhere. You cannot get ideal DC in power electronics, because power electronic level, all choppers, phase control rectifiers are not ideal DC. But yes, please understand that in my subject, we assume first ideal DC, we get in cells, batteries initially, and also precision voltage regulators in electronics. There we may get ideal DC, and for ideal DC, dV by dt is 0 and di by dt is 0. In resistor, it will work, but inductor short, capacitor open in steady state. Okay, now that is the first thing. Then, sir, before we go to part 2, now chapter 4. See, there is a small chapter 4, which is basics of time variance. Basics of time variance. That means in this chapter, we will analyze circuits for time varying waveforms. In this chapter, we will analyze circuits for time varying waveforms. Like, for example, I will give triangular waveform. Okay. Then I may give some square waveform. Okay, some square waveform. Symmetrical square waveform. Okay. Then sometimes okay, I will give some unidirectional sawtooth waveform. Please understand. So everybody what you see is, see, this chapter 4 is also a part of circuit theory, but this chapter 4 is about basics of time variance. Okay, chapter 4 is about basics of time variance. What I will do in this chapter, I will give some time varying signals. But in the first part of subject, I teach only DC circuit analysis, ideal DC. Okay, in the first part of subject, I teach only ideal DC. Okay, for ideal DC, only resistor will behave, but inductor acts like short and capacitor acts like open. Then I go to basics of time variance in chapter 4. It is a very small chapter, but here again, resistor is working normally. Resistor is normal again. It is again homogeneous proportional. Homogeneous or proportional. What does it mean? Like triangular voltage will give triangular current, square voltage will give square current, sawtooth voltage will give sawtooth current. So its response is proportional and homogeneous, obeying Ohm's law. But now what happens? This inductor and capacitor starts working. They start working. They start working for these time varying signals, where we analyze inductor as V is L di by dt and capacitor V is 1 by C integral I dt. Okay, so that we will plot, okay, by using Ohm's law. This is Ohm's law that I will teach you. So this chapter 4 is an introduction to time variance, where we will give miscellaneous signals and understand especially how inductor and capacitor will behave. Once you know the understanding of inductor capacitor basics, okay, basics, then we'll go to part 2. Then we will go to part 2. Now part 2 of my subject is steady state AC circuit analysis. Okay, it is steady state AC circuit analysis. AC circuit analysis. Okay, now steady state AC circuit analysis is called as sinusoidal circuit analysis. That means we are declaring indirectly the number one AC waveform is sinusoidal waveform. The number one AC waveform is a sinusoidal waveform. The number one AC waveform is a sinusoidal waveform. Okay, the number one AC waveform is a sinusoidal waveform. Okay, why this is number one, what is the reason, we will discuss in chapter 5. So first part 1 to 3 chapters is DC steady state. Okay, now then second part is AC steady state. But before we come to this chapter, a small introduction on time variance. But in this chapter for ideal AC, which is sinusoid, I will tell you why number one AC waveform is sinusoid. That I will discuss later. But here everything will work. Again, resistor is homogeneous proportional. Homogeneous proportional. But I will call here as in phase element. In phase. That means in resistor it will not create any phase shift. Voltage and current are in phase. But inductor, yes, inductor is a lagging element. That means in a pure inductor, current lags voltage by 90 degrees. In a pure inductor, current lags voltage by 90 degrees. And in capacitor, it is a leading element. That means in a pure capacitor, current leads voltage by 90 degrees in phase. Now all this I will prove mathematically with Ohm's law, and then I will explain. So here phasor notations will come. Okay, here what happens now, sir, when we do this phasor analysis, okay, with J operator will come. So another big area for electrical engineering people is AC steady state. Okay, like DC steady state is one big area, which is number one waveform at electronic level. AC steady state is another big area where number one waveform at power level. So all our power system machines in AC, we talk ideal AC, that is sinusoid. There we do phasor analysis. And resistor is a homogeneous proportional component in phase, and inductor is a lagging element, and capacitor is a leading element. Okay, that is in inductor, current lags voltage by 90 degrees in a pure inductor, and in capacitor, current leads voltage by 90 degrees. Okay, so this is part 2, which I will say it is another, yeah, I will say easily 40% and above. 40%. Okay, easily 40%. Even DC, I will say this is 35 to 40%. Okay, I will even say this is also 40%, sir. Marks wise, let us stop. Okay, DC will go up to 40. AC steady state also will go up to 40%. Like out of 10 marks, 4 marks DC, 4 marks AC, which includes resonance, magnetic circuits, etc. Then part 3, yes, part 3 is the miscellaneous topics. Like I will say, part 3 will be about transient circuit analysis. Transient circuit analysis, which I also say dynamic response of circuit. Dynamic response of circuit. Steady state static responses are DC and AC, but this is dynamic response. That means here switch concept will come. Okay, suppose to any network, yes, to any network, I will turn on suddenly. Okay, turning on suddenly by closing a switch is like dynamic concept. I will turn on suddenly. Okay, yes, I will turn on suddenly. Okay, then here based on the order of circuit, if it is first order exponential, if it is second order, 3 types: overdamped, critically damped, underdamped, transient or dynamic behavior. Here stability of the network. So here, yes, non-linear mode of operation. Okay, will come there. First order circuits, second order, or even higher order we study. Okay. Then here stability of networks will be studied, etc. Okay, etc. So this is easily I can say, yeah, this is like 20%, 20% in terms of content. But apart from that, I will say miscellaneous topics. Then topics like two-port networks. Okay, two-port networks. Then I will say after two-port networks, graph theory or topology. Okay, locus diagrams, etc. are miscellaneous topics. Miscellaneous, but these all are included in this 20%. Okay, these all are included in this 20%. So I'm briefing out everybody. My subject, yes, I will be considering 3 parts. Okay. So part 1 is DC circuit analysis, which is around 40% of content as well as marks. But there's a small chapters on basics of time variance. That is a small chapter, sir, but important to understand inductor capacitor. Then I will go to AC steady state analysis. That is also another 40%. Then I will come to transient circuit analysis, dynamic response of circuits, where nonlinear mode of operation, first order, second order circuit, stability of networks will be tested, which is very, very, very interesting mathematically. Then miscellaneous topics like two-port networks, topology, locus diagrams, etc. keep coming. Even duals and duality, I will mention that. Duals and duality, etc. will come. Okay, all this will be coming. Okay, and in AC steady state also, we have both single phase and 3 phase. So that all will be included. So here we have 3 parts, but basically 3 parts, and miscellaneous topics will be merged in between. So that is how my subject is having a lot of dominance and so many topics. Please understand that. It is having so many topics. That is the first thing that you should know. Okay, that is having so many topics and subtopics inside. Okay, na? Chalo, now I am starting with my syllabus. So everybody please understand I am starting with my syllabus. Okay. Now, see, what is this? You are raising your hand. What is this? Prithvi, what is the problem? Maybe sometimes you unknowingly do, but it disturbs. Okay. Anyone want to ask anything? But I told Nasser doubts only after the session is over. Prithvi, Asfani, Vishnu, please down your hand. Ajit, please down your hand. Anything you want to ask, but not now. I told Nasser, technical doubts, anything you ask after the class. Suppose something you have a doubt, you note down on a paper. Everybody put a notes at the same time. Don't just watch like a movie. Prithvi, you are still not putting down your hand, but everybody see here. What I would say is, while listening to me, you take a pad, papers, and a pen. Write along with me, sir. When I ask a problem, though I will share notes and you can have this video again. But what I suggest is, please take a pad, paper, and pen. And whenever I am asking any question, do it, sir, please. Okay, now do it. That is what I am expecting from you. I really want that. Everybody should do that. Okay. Just listening to a video, it won't come, sir. This subject won't come like this. Okay. If you just listen to video, it won't come like this. Okay. That is what I would expect everyone to do. Okay. Chalo. Now I'm starting my syllabus here. So yes, first question is, okay, what is so greatness about electrical energy? Okay. We are all electrical engineers. So what is the greatness about electrical energy? Okay. Now, electrical energy is one of the most dominant and superior forms. Please understand, electrical energy is one of the most dominant and superior forms because of many reasons. First reason is interconvertibility. Okay, and second reason is transportation. Sir, if someone asks, what is so great? Yes, what is so great about EEE branch, or what is so great about electrical science? Then the first thing you should argue is, yes, electrical energy is superior and dominant because of many reasons. Yes, superior and dominant because of many reasons. But the two outstanding reasons why this energy is very powerful is, one is interconvertibility and second is transportation. So if someone asks you, what is so great about electrical energy? Yes, you should mention first is interconvertibility and second is transportation. Yes, first is interconvertibility and second is transportation. Because of these two reasons, this is an outstanding and ultimate energy. Okay, interconvertibility and also transportation. Now, what does it mean? Now, what does it mean? Now, what is interconvertibility? Now, interconvertibility is a process. Yes, interconvertibility is a process where you can convert different forms of energy into electrical energy. See, interconvertibility is a process where we can convert different forms of energy into electrical. Like I can say, yes, we can convert heat energy to electrical, like thermoelectricity, okay, etc. We are doing heat electric, even gas plants. Gas plants directly hot gases are given to turbine. Gas turbine is very special, please. Okay, it is a high pressure turbine. Then we can convert mechanical to electrical. That is what our alternators do. All mechanical, thermal station, hydro station, mechanical to electrical. Then we can give solar panel, solar to electrical. We can do wind energy. Okay, wind plants. Then we can convert even chemical to electrical. Chemical like batteries, etc. So many ways are there, sir. So as of now, there are so many ways like tidal, nuclear, biomass. Okay, so many ways are there. So the beauty of this energy is we can convert different forms of energy into electrical energy, and we can convert them back. Interconvertibility. Now from electrical, we are getting heat again. Our heaters, geysers do. From same electrical, we are getting mechanical again. Our motors will do. From same electrical, we are getting light. From same electrical, we get wind, fans, blowers, ACs. And from same electrical, we also get chemical, like all our electrometallurgical process. Okay. Yes, refining industries, etc. So that is a beauty, sir. It is interconvertibility. So this energy is highly flexible in conversion. Highly flexible in conversion. That is a beauty, sir. No other energy is flexible as electrical. So the energy in this world can be available in many forms, but you can use all those forms to convert first into electrical, like heat to electrical, mechanical to electrical, solar, wind, chemical, biomass, nuclear, tidal. So many are there, sir. And the beauty is you can convert them back, like electrical to heat, electrical to mechanical, electrical to light, electrical to wind, electrical to chemical, etc. So the unique feature, like in your house also, you see, sir, you are converting electrical into different forms or not? Yeah, you convert into light, you convert into sound, you convert into, ACs, wind. So entertainment, our television, cell phones, everything work with electrical. So that is a beauty, that this energy is highly interconvertible. That is the first reason. Second reason is transportation. The only energy in the world, okay, where we can generate, and transport, yes, first in bulk quantities, and that too for longer distances, that too in the most economically is electrical, sir. No other energy in the world can do it. The only energy in the world where we can generate and transport in bulk quantities, okay, longer distances and most economically. Of course, EC people do this at signal level, that is communication, but electrical do at power level, that is power transmission. Okay, but we are all electrical now, sir. We should talk electrical side applications. Bulk quantity is a bulk energy. So the only energy in the world where we can generate and transport in bulk quantities, that too for longer distances, and that too in the most economically, is electrical. Like I will give an example. Our 1 unit of electrical energy, yes, our 1 unit of electrical energy is 1 kilowatt hour. What does it mean? It is 1000 watts consumed in 1 hour. 1000 watt consumed in 1 hour. But such a huge energy with subsidy from the government, we are getting for only ₹3 per unit in most of the India, in suburban, urban, and rural areas for domestic application. This is for domestic, I will say, domestic. Okay. So what I want to say, this huge energy, which is 1 kilowatt hour. What does 1 kilowatt hour say? 1 kilowatt hour is 1000 watts consumed in 1 hour. Okay, 1 kilowatt hour is 1000 watts consumed in 1 hour. And such a huge energy we are getting for hardly ₹3 at domestic level with subsidy from the government. But of course, no other energy is as cheap as electrical, sir, because 1000 watts continuously used for 1 hour is 1 kilowatt hour. And which energy can be as cheap as electrical, sir? No other energy except electrical. So that is the reason I say it is also highly economical. Of course, commercial tariffs and industrial tariffs are very high, but generally domestic is very, very cheap. Okay, now that is only energy in the world where you can generate and transport in bulk quantities, that too for longer distances, and in the most economical way is electrical. Please understand. Okay, that is a thing you have to understand. Now, we are learning about this electrical energy. Yes, electrical energy, both at signal level and power level. Okay, we are learning first at power level. Okay, power level. Who is learning in power level? EEE branch, electrical engineering branch. Doubly I will write. Okay, we learn in power level. Power level means what? High voltage in kilovolts, high current up to kiloamperes. Okay, power is also, yes, kilowatts to megawatts, even megawatts to gigawatts. Okay, gigawatts, high power. But our frequency in power system is 50 hertz. Please understand, sir. So we are now learning about this great energy called electrical energy, both at power level as well as signal level. Okay, we are learning this great energy called electrical energy, both at power level as well as signal level. What does mean power level? What does mean power level? Power level is high level. Power level is high level. That is high voltage, high current, high power, but frequency is 50 hertz. Okay, high voltage, high current, high power, but frequency is 50 hertz. Okay, okay, now that is about electrical level, high power level we call. We also learn this energy at signal level. We also learn this energy at the signal level. Okay, signal level. Which branch learn this signal level? Like ECE or even instrumentation people, sensors, etc., transducers. Signal. What is signal level? Signal level is low level, like millivolts to few volts. Okay, current is microamperes. Power is milliwatts to few watts. But their frequency in communication is very high. That can be in kilohertz, megahertz, and even gigahertz in communication. Okay, so we are learning this energy both at power level as well as signal level. Okay, in power level, everybody please understand, in power level, high voltage, high current, high power, but frequency at power system level is 50 hertz. But we also learn this energy at signal level. What does signal level means? Low voltage, low current, low power, but frequency in communication and signal processing is very high, like kilo, mega, giga. Like we have radio frequency, audio frequency, video frequency range like that. Now, because of this discrimination in power level versus signal level, the performance parameters are different. Now, for EEE people, because we are talking at power level, high level, what are the factors which affect? Yes, efficiency, power factor. Okay, I will write neatly. Okay, efficiency is eta. Okay, efficiency, power factor. Okay, safety, reliability. Okay, reliability, cost. Okay, safety, reliability, cost. Okay, percentage, voltage regulation, losses, etc. are important. Okay, that means if you are talking this energy at power level or high level, then what are the factors which decide the performance of a system? So at power level, when we talk, everybody, this is introduction class. Don't get panic. Okay, this is introductions are basics, all basics introduction. Okay, don't worry. Slowly I will teach, sir. But this is an introduction class, na sir, where we are starting, what is necessary, what is the background work, such things I am teaching. So don't worry, sir. After some 6 to 8 hours, you'll get very comfortable level. Don't worry. So then I will go very carefully. But this is still important, that why we are learning this subject, what is the necessity to learn this subject, what are the different types of components, all this we are learning today. So please cooperate, sir. Don't worry. At the same time, you will get my notes, you will get videos. So again and again, listen, don't worry. So this energy we are learning both at power level and signal level. Power level means high level, high voltage, high current, high power. But power system frequency in India is 50 hertz. So when we are analyzing and designing any component power level, what are the parameters you should look into? Efficiency, cost, power factor, safety, reliability, voltage regulation, losses. Okay. Then if you are understanding any component at signal level or low level, okay, signal level or low level, what are the parameters there? Their parameters like precision, accuracy, accuracy, speed, compact, portable, precision, accuracy, speed, compact, portable, okay, intelligent, control, okay, control and intelligence, okay, precision, accuracy, speed, compact, portable, control and intelligence. That means when you are talking about signal level components, when you are talking about signal level components, there we require precision, accuracy, speed, compact, portable, control, intelligence. Okay, that is what we require. Like now, I'll use such examples. Now listen carefully. Like our transmission lines are there. Now transmission lines are power lines for electrical people. They are also telephone lines for EC people. In power line transmission for electrical, we calculate efficiency, losses, fault analysis, regulation, power factors, etc. Yes or no? But the same transmission line EC, for them speed of communication, baud rate, okay, okay, how intelligent it is controlling a device, high gigahertz, high speed processors, okay, such things we talk. Suppose you buy a cell phone versus air conditioner. See, air conditioner is a power level product. So when you buy air conditioner, what you see? Star rating. That star rating will improve. 5-star rated AC means high efficiency, high power factor, inbuilt voltage regulator, less losses, high efficiency. All these are the meaning. But if you buy a cell phone, in cell phone we are not interested in cost and efficiency. Now, sir, cell phone we buy for precision, accuracy, speed, compact, portable, etc. So understand the difference. So power level in air conditioner, where we look into these parameters like efficiency, cost, etc. But signal level like cell phone, we look, I need more RAM. RAM in cell phone is for more speed and accuracy, compact, portable, control, etc. So that is a difference. When you buy an air conditioner, it is a power level product. When you buy a cell phone, it is a signal level product. Now, as electrical, we study both also, sir. Like which subjects come in power level, everybody listen, which subjects come under power level? Your power system, power electronics and machines come under power level. Yes or no? Yes, your power system, machine and power electronics come under power level. Then which subjects come under signal level? Analog, digital, microprocessor, signals and systems, etc. come under signal level. Of course, networks, controls and measurements come both level. Okay, now remember that. Networks, control and measurements come both level, but generally power level subjects are machines, power system, power electronics. Signal level subjects are analog, digital, microprocessor, etc. Okay, now? So as electricals, we are learning both, sir, but understand the difference. When we analyze a component at power level, we look into those parameters, but when we analyze a component at signal level, we look into these parameters. Okay, now? Now there is a big difficulty with electrical engineering. Yes, we all say electrical engineering is tough. Yes, that is a thing we always say. We say electrical engineering is tough. Why electrical engineering is considered as tough? Yes, there is a reason for it. Electrical engineering is tough because I say, yes, all the parameters cannot be sensed, because in understanding electrical engineering, all our 5 senses don't support, please understand, don't support in understanding electrical science. Simple answer. If someone says, sir, is electrical engineering tough compared to other branches? I honestly say yes. Yes, I honestly say to understand electrical engineering, it is tough. What is the reason? Yes, my reason to say why electrical engineering is tough is, yes, my reason to say why electrical engineering is tough is because in understanding this great energy, everybody, in understanding this great energy, all our 5 senses don't support. Now God gave us 5 senses, sir. Okay, God gave us 5 senses. What are the 5 senses? Panchendriya we call. Okay, 5 senses are our Panchendriya. Okay, now what are our 5 senses? Yes, Panchendriya. Like sense of touch, sense of listening, sense of talking, sense of touch. Okay, sense of seeing. Okay, touch, seeing, smell, taste, and hearing. All this will fail in electrical engineering, sir, because you cannot see our signals directly. Okay, there is so much of flux and charge around us, but we cannot sense it, we cannot feel it, we cannot see it, we cannot taste it, we cannot taste DC and AC voltage. Will it make any difference? So please understand. I always say to the students, like, are electrical engineering tough? Yes, it is tough, sir. Let us accept honestly. But what is the reason? Because in understanding this great energy, all our five senses don't support. Please understand. In understanding this great energy, all our five senses don't support. There are five senses, okay? Like sense of touch, sense of seeing, sense of smell, sense of taste, and sense of hearing. Nothing will work. Then how to learn? Then how to learn electrical engineering? Yes, how to learn. Okay, how to learn electrical engineering. Yes, we can learn electrical engineering first. Follow notations. Follow rules and notations. Notations are rules, okay, that we have to follow notations, okay. Now I will say this is notations, okay. Second is, yes, be strong in mathematics. So the secret of learning electrical engineering is, first you should follow notations, and then you have to be very strong in maths. Mathematically we can learn, though our senses are not supporting. But how to learn electrical engineering? Yes, follow notations, that are the rules, and also be strong in maths. Now what are notations? Example 1 for notation. Now in my subject, in any element, yes, in any element, if current leaves positive terminal of voltage, then I say it is a source. In a source, power delivered is positive watts. Power delivered is positive watts. Okay. In the same component, suppose current is entering the positive terminal of element. Then it is a sink. Then power delivered is negative, or power absorbed is positive watts. Please understand the meaning. Everybody, notation example I am giving. So that means taking polarity for voltage and even direction for current is a notation. Taking polarity for voltage and direction for current is also notation. So in any element, if current leaves the positive terminal of voltage, it is called as a source, sir. Current leaving the positive terminal of voltage is called a source, and current entering the positive terminal of voltage is sink. Okay, so current leaving the positive terminal of element is a source, and current entering, okay, current entering the positive terminal of an element is a sink. So current leaving positive is source, current entering positive is sink. In a source, power delivered is positive. In a sink, power absorbed is positive. Please understand the difference. In a source, current leaving is positive. In a sink, current absorbed is positive. Okay, that is how we talk. Okay, now that is how we talk. Okay, so that is another example of notation. Now, example 2 I will give. Example 2, yes, is about a permanent magnet. Suppose permanent magnet is there. Now, permanent magnets are either available from rare earth metals like samarium, cobalt, black color one, or it is artificially made with alnicos. Suppose there is a bar magnet. Listen to this, sir. There is a bar magnet. Okay, now this has got north pole and south pole. Now we cannot see anything now, sir. That is what our senses don't support. We cannot feel the flux. We cannot see the flux. So we gave a notation. What is the notation we are following? We say that flux leaves north pole externally and enters south pole externally. So flux leaves north pole externally and enters south pole externally, but internally it will go from south to north. Similarly here also. Flux leaves north pole externally and enters south pole externally. Internally it will go from south to north. So how many flux lines leave north pole? That many flux lines enter back. How many flux lines leave north pole? That many flux lines enter back. Okay, that is the meaning, sir. Flux leaves north pole externally, enters south pole externally. Internally it go from south to north. That is the meaning. So how many flux lines leave north pole? Okay, that many flux lines will enter back. That is law of conservation of flux. So we are taking orientation of flux is also notation, sir. Yes, taking the orientation is also a notation. What is that? Because we cannot see. We have to take such things and learn. Like for voltages, polarity, for currents, direction, whatever may be the signal. It is a DC signal or AC signal or sinusoid or ramp or parabolic. But we have to take a polarity and direction, sir, for voltage and current respectively. Similarly, flux cannot be seen. Flux cannot be felt. Our human body is not in a position to recognize it. Our senses don't support. Then how to take a notation and argue? Yes, we say flux leaves north surface externally and enter south surface externally, and internally it will go from south to north. Okay, internally it will go from south to north. Externally it will go from north to south. Internally it will go from south to north. And these are closed contours, but that is a notation. Taking direction flux is also a notation. Okay, now that is a very, very important thing, like notation. Now, another important example I will give you. Yes, another important example I will give you. Like Ampere right hand thumb rule. Ampere right hand thumb rule. That is also wonderful rotation, sir. Ampere right hand thumb rule. What does it say? Yes, in any straight current carrying conductor. Yes, indicated by the thumb. Because here straight is current, not thumb. Right hand only you have to take, sir. All right hand. In any straight current carrying conductor, if thumb is indicating the current direction, then the closed fingers indicate the orientation of flux. Okay, the closed fingers indicate the orientation of flux. Actually, these are circular cylindrical lines, but these closed fingers indicate the orientation of flux. So this is a symbol. This in fact is a symbol of IEEE. This in fact is a symbol of IEEE, because our IEEE symbol is right hand thumb rule, sir. See, this is the symbol of IEEE. Of course, here flux and current direction are interchangeable. This is the beauty of notation. Our IEEE symbol is Ampere right hand thumb rule. How many are IEEE members? You know, na, sir. See, this is the symbol of IEEE. Like if flux is straight, closed fingers are current. If current is straight, indicated by thumb, closed fingers are flux. Vice versa. Here current is straight, so thumb is current, closed fingers are flux. But in a coil winding, closed fingers are current, then thumb is flux. You can interchange. But see how beautiful this notation is. So I told how we are learning this electrical energy. So we learn this both at power level and signal level. Power level subjects are machines, power system, power electronics. Signal level subjects are, yes, what are signal level subjects? Yes, signal level subjects are analog, digital, microprocessor, signals and systems, etc. But my subject, network theory, control systems, power, these measurements, we do both levels, sir. Signal level also we teach, power level also we teach. Common subject. But because power level, we are interested in efficiency, power factor, etc. Signal level, we are interested in precision, accuracy, speed, etc. Like you give example like air conditioner versus cell phone. Air conditioner, power level. Cell phone, signal level, like that. And how to learn this tough subject then? Yes, we follow notations, rules, and mathematics. Okay, what are notations? Yes. What are notations? Yes, please understand. Notations, these are our own rules that we have built up in electrical engineering, with which we can learn things like taking polarity for voltage, taking direction for current. Okay, with that, what is source, what is sink, then permanent magnet, flux orientation. Then here also see obeying Ampere right hand thumb rule, etc. All these come under notations. Because we cannot see flux, we cannot see everything, na, sir. We have to follow these notations. Okay, and with these notations only we get. Okay, like notations are everywhere required. Okay, please understand. Notations are required everywhere. Now, let us take circuit model example. Okay, circuit or network model example. Network model example. Okay, now what does it mean? Like example, we are modeling our power system transmission line. We are modeling our power system transmission line. Power system transmission line. Let us say we are modeling our power system transmission line. Now our transmission lines are our electrical power lines. We step up voltage with less current and transport, and we step down back. Like our transmission lines are ACSR conductors. So they have resistance or not? Yes, they have resistance. Okay, now they have resistance. Okay. Yes, our power transmission lines have resistance. Do they have inductance? Yes, they also have inductance. They also have inductance. Okay, flux linkage, internal, externals. Do they have capacitance? Yes, they also have capacitance. They also have capacitance. They also have capacitance. Okay, so yes, our power system transmission lines, understand, the series components are inductor, capacitor, and the shunt component is capacitance. Of course, there is leakage conductance also. That leakage conductance I am neglecting right now. But yes, where is RLC? What does RLC represent? See, what does RLC represent? I want to know, argue here. Resistance represents linear time invariant property of matter. Property of matter. Okay, resistance represents linear time invariant property of matter. Inductor represents electromagnetic property of matter. Electromagnetic property of matter. Okay, na? Electromagnetic property of matter. And capacitor represents electrostatic property of matter. Electrostatic means charges at rest. Electrostatic property of matter. That is the meaning. So everybody should understand that circuit or network model. Okay, in circuit or network model. Yes, please understand this. In circuit or network model. Okay, everybody, please listen to this. That our power system transmission lines. Yes, in our power system transmission lines are RLC networks only. But what are they? What are these three parameters? They are the fundamental passive properties with which we model everything in the world. So what is RLC? Yes, my subject is full of RLC. Okay, na? My subject is full of resistors, inductors, capacitors, and their analysis only. Analysis for DC, analysis for AC, etc. Okay, so what does they mean? What does it mean? Yes, please understand that resistance represents the linear time invariant property of matter. Resistor represents linear time invariant property of matter, and this passive property's behavior is independent of frequency. And this passive property behavior is independent of frequency. Inductor represents electromagnetic property of matter. Okay, inductor represents electromagnetic property of matter, and capacitor represents electrostatic property of matter. Okay, so inductor represents electromagnetic property of matter, and capacitor represents electrostatic property of matter. So understand that. So what does it mean? Yes, our RLC parameters represent everything in the world, like transmission line. Our power system transmission line, short line, medium line, long line, we model na, sir. But those lines which transport our energy, okay, by stepping up voltage, stepping down current, minimum losses, etc., where series components are resistor, inductor, and shunt components are capacitor and conductance. Of course, here conductance I am neglecting, leakage conductance. But here, what they represent, resistance represents the linear time invariant property of matter, independent of frequency. Inductor, what it represents? Inductor represents electromagnetic property of matter. Okay, inductor represents electromagnetic property of matter, and capacitance represents electrostatic property of matter. So wherever these properties are there, model them. Like our ACSR conductors, that is aluminum core, steel reinforced. You know, resistance is there to the wires, and electromagnetic property, flux linkages will come internally, externally, we calculate inductance. And also our transmission lines charged with respect to ground also exhibit capacitance. Yes or no? So we model them. That is the meaning. So network theory is all about modeling our physical systems into RLC and analysis. Then we do DC steady state if it is a DC excitation. Then we do sinusoidal steady state excitation, single phase, three phase. And also we do transient analysis like switching, turning on, turning off, etc. Okay, that is the meaning there. That is what we learn. Then I will give another example. Like capacitor. Example, capacitor. Okay. Now we know capacitor represents what? Electrostatic property of matter. Capacitor represents electrostatic property of matter. Then how to learn this? I told Nasser how we are learning electrical engineering by using notations and maths. Okay, we use notations and maths. Example I will give. Like capacitor, I will teach with notation. What is the notation? First symbol. Capacitor symbol is like this. Okay, capacitor symbol is like this. And globally it is a passive element. It is a sink. So in a sink, you know, the direction in which current enter is taken as positive. That is a notation for sink. So capacitor represents what? Electrostatic property of matter. Okay, everybody. So capacitor represents electrostatic property of matter. Okay, what are the notations? Notations include the symbol, like capacitor symbol is like this. Okay, na? And also in a capacitor, sink notation, the direction in which current enter is taken as positive. Like I told you, Nasser, sink notation here. Yes, here I gave Nasser sink notation, current enter positive, like that. Okay, so that is a notation. So we represent it symbol, units, and mathematics. Now, how to learn this? How to learn this? Yes, mathematically. Mathematically, we learn this. What is the meaning mathematically? Like example, Ohm's law. Example here again, Ohm's law. We learn about capacitor mathematically, not any physical explanation. So what is the Ohm's law for capacitor? See, the Ohm's law for capacitor is, I is C dV by dt. Now this is the Ohm's law for capacitor. So for capacitor, I is C dV by dt. Okay, this is the Ohm's law for capacitor. I is C dV by dt. Okay, now, so this is the Ohm's law for capacitor. Okay, so in a capacitor, we learn mathematically, that is by Ohm's law. Okay, in a capacitor, that is a voltage and current, and I is C dV by dt. Okay, now from this only we explain everything. Like for ideal DC, now listen, for ideal DC, okay, like for ideal DC, okay, for ideal DC, you know ideal DC look like this, na sir? Ideal DC, how it will look? Okay, for ideal DC, I will write like this here. Yes, for ideal DC signal. Now ideal DC signal look like this. Okay, voltage versus time. It will look constant voltage. Okay. Now here for constant voltage, what happens here? dV by dt is 0. When dV by dt is 0, I is also 0 in a capacitor. Yes or no? So I is 0 means capacitor acts as open circuit. Yes, capacitor acts as open circuit in DC steady state. Yes, capacitor acts as open circuit in DC steady state. That is the first thing. Then we give ideal AC. What is ideal AC? Ideal AC is a sinusoid. Now ideal AC waveform look like this. Okay, ideal AC waveform look like this. Okay, it is a sinusoidal signal. All this will prove, sir. Don't worry. This is all introduction. So ideal AC waveform look like this. It is a sinusoidal. Okay. Then for ideal AC, after applying the Ohm's law, like V equal to, see if you take V equal to Vm sine omega t. Okay, if you take this V equal to Vm sine omega t, substitute, you will get this current I equal to something like Im sine omega t plus 90. You will get I equal to Im sine omega t plus 90. That is what mathematically I will prove this in 5th chapter. Don't worry. But yes, what I will say, it is a leading element because current is leading voltage, leading element. Okay, now current is leading voltage. So how we are learning capacitor? First of all, capacitor represents electrostatic property of matter. Okay, now wherever electrostatic phenomena is there, model with capacitor. Okay, now wherever electrostatic phenomena is there, model with capacitance, like transmission lines have capacitor, diodes have junction capacitors, or filters have capacitors, power factor correction components. Now, how to learn capacitor notations and maths? What is the notation? Like taking symbol. Yes, taking symbol, taking polarity and direction. Taking symbol, taking polarity and direction. Okay, and we learn mathematically by using Ohm's law. Okay, now then how to learn? Yes, we learn mathematically by using Ohm's law. Like for ideal DC, ideal AC. Okay, now ideal DC, yes, ideal DC, it is dV by dt 0. Okay, capacitor acts as open circuit. And ideal AC, like Vm sin omega t, current leads voltage, okay, by 90 in a pure capacitor. Okay, now, so that is how mathematically I will teach, sir. Mathematically, we will learn everything in this subject as well as electrical engineering, respecting notations. So that is how easy to learn mathematically. And everywhere small mathematics, derivations, conclusions will come. So that is all. For example, ideal DC, capacitor acts as open circuit in steady state. Ideal AC sinusoid, current in a pure capacitor leads voltage by 90. That is how I will teach. But I will ask a question. Yes, the question is, does really current flows through capacitor? Okay, does really current flows through capacitor? Does really current flows through capacitor? Okay, does really current flows through capacitor? My answer is no. Current never flows through capacitor. Then how capacitor is working? Please understand this. Does really current flows through capacitor? No, sir. Actually, you take an example of parallel plate capacitor. Now this parallel plate capacitor is separated by dielectric. Okay, this parallel plate capacitor, okay, is separated by dielectric. So there is a dielectric material inside. Okay, I'm showing like this. This parallel plate capacitor has dielectric inside. Okay, dielectric. Okay, this parallel plate capacitor has dielectric. Now dielectrics are very special insulators. Okay, these are special insulators which exhibits polarization. Polarization. Okay, please understand what are these dielectrics. Dielectrics are special insulators which exhibit polarization. Like examples: mica, resin, oil, glass, electrolyte. Electrolyte means weak acids. What does electrolyte means? Electrolyte means weak acids. So now what happens here? Listen carefully. Does really current flow through capacitor? My answer is no. Then how it is working? They work with the principle of polarization. The phenomena is polarization. So what does capacitor has? A parallel plate capacitor like aluminum plates. In between these plates, there is a dielectric. What is dielectric? Dielectrics are special insulating materials which exhibits polarization. Which materials are like dielectrics? Like mica, resin, oil, glass, electrolytes, etc. Okay. Now this exhibits polarization. What is the meaning? Suppose, now listen carefully. Suppose I give positive voltage A and negative B. That means I am giving voltage across AB with A positive with respect to B. Then what happens due to this? Yes, due to this polarity, everybody, due to this polarity, now the electric field will flow from plus to minus plate through the dielectric material. Okay, from plus to minus through the dielectric plate, the electric field will flow. Then what happens? Then all the dipoles will align. That means this dielectric have dipoles, na sir, they align in the direction of field. They align in the direction of field. Okay, all will align in the direction of field where, yes, where plus minus, they will align in this way where this plate is positive and this plate is negative. That is how polarization takes place in the dielectric material where all the dipoles will align in the direction of field, and that is how the plus will accumulate in the A plate and minus in the B plate. That is how material gets polarized. Now suppose you reverse the polarity. Now what happens now, sir? Suppose you reverse the polarity. Like in AC signal, every positive half cycle, negative half cycle. Suppose now the same capacitor, which is a parallel plate capacitor, which is having dielectric material, of course, like mica or resin or something. Now you give reverse polarity here. Now suppose you give reverse polarity. Like you make a B positive with respect to A. Then what happens is, yes, the electric field will orient in the ulta direction. Now it is going upwards from B to A in the material, in the dielectric material. So when it is going upwards, now all the dipoles will align. Now all the dipoles will align in the reverse direction. Okay, all the dipoles will align in the reverse direction. All the dipoles will align in the reverse direction. So what happens there in the reverse direction? Plus minus, 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 plus minus. So all the dipoles will align in the reverse direction, and thereby automatically this plate become positive and this plate become negative. See, that is the meaning, sir. When I give this polarity, the electric field inside the dielectric will flow from A to B, start at A and terminate at B. As the field is orienting down, the dipoles also will align in the direction of field, where A plate becomes positively charged and B plate becomes negatively charged. The same thing when I reverse the polarity, like in a sinusoid negative voltage or negative cycle, when B is positive with respect to A, the electric field will go upwards and all the dipoles will align in the ulta direction and B becomes positive and A become negative. So that is how, due to polarization of the material in the dielectric, yes, the charge gets accumulated, and that is how the capacitor will work. But the truth is, there is an insulator inside the plates. It won't conduct. That is why this current in capacitor is called a displacement current, but not conventional. See, in normal wires, so I want to give that. So in capacitors, I will say in capacitors, we call this as displacement current. Yes, displacement current. It is not the physical charge which is transferring. We call this as displacement current. And why this displacement current is happening? Due to polarization. But in normal wires, in normal conductors, in normal wires or conductors, okay, in normal wires or conductors, that is called what? conventional current, yes, where charge physically transfers. Please understand, everybody. Please understand. See, what I want to say is how this is working. That is what everyone should know. See, capacitor. See, I'm giving an example, sir. All this is an example to understand. See, what is RLC? RLC represents the three fundamental passive properties with which we model everything in the world. RLC represents the three fundamental passive properties with which we model everything. Where resistor represents linear time invariant property of matter, inductor represents electromagnetic property of matter, capacitor represents electrostatic property of matter. Okay, resistor represents okay, linear time invariant property, inductor represents electromagnetic property, and capacitor represents electrostatic property. Okay, so then how to learn about capacitor? Yes, how to learn about capacitor? Capacitor represents electrostatic property of matter. We learn with notations and max. So what are the notations for capacitor? Yes, symbol, units, passive notation, and how to learn mathematically like Ohm's law. Like Ohm's law for capacitor is I equal to C dV by dt. And from this only now, sir, ideal DC, we say capacitor acts as open circuit because dV by dt is 0, I is 0. And for ideal AC, if you put V equal to Vm sin omega t and derive now, sir, you will get this expression. That I will derive in 5th chapter, but you will get something like this, like Im sin omega t plus 90. What does it say? Current will lead voltage by 90 degrees. It is a leading element. So now for any signal, you give me ramp signal, parabolic signal, triangular signal, every signal I will teach with Ohm's law. That is how electrical engineering we are learning with notations and max. That is the best example I want to give. So electrical engineering we are learning with notations and max. But really, does current flow through capacitor? My answer is no. But see the difference, how simply mathematically we are learning like this. But physical phenomena is completely different. What happens inside capacitor is not the conventional current. It is due to polarization, the displacement current. But whatever may be the secret inside, but I will teach mathematically. That is what I want to highlight, sir. That is what I am highlighting here. Why we are learning mathematically? Because there is an easy way. So electrical engineering, though it is a tough, but we can learn mathematically in an easy way. So if you are good in mathematics, now, sir, this is an easy branch. That is my conclusion. If you are good in mathematics, like Laplace transform, Fourier series, Fourier transform, Z transforms, phasor analysis, algebraic equation, matrices, your electrical engineering becomes simply superb. So like how capacitor is working, when you give positive voltage, the field flows from plus to minus and all the dipoles will align in one direction. Okay, and when you give minus plus, the field will ulta and dipoles also will reverse and becomes ulta plates. That is how by polarizing the material. Yes, by polarizing the material, the charges also get polarized, and that is how the capacitors will work. But in normal wires, that current is called conventional current. But in capacitors, the current is called displacement current. That is a meaning. So that is an example I want to give. So this is mathematical. This is science. Mathematics is what engineers follow, and science is only physics. Please understand. So this is mathematics. Engineers follow, and this is science. Now, what does I want to conclude here? Yes, the conclusion of this example is, yes, I would like to say engineering is, okay, engineering is application of science. Okay, engineering is application of science and analyzing. Okay, and analyzing by mathematical modeling. Okay, mathematical modeling. Okay, that is a simple answer. So engineering is application of science and analyzing by mathematical modeling. That is what is my discussion, sir. So engineering is application of science and analyzing by mathematical modeling. Okay, everybody, I'm just taking 5 minutes break. You also have just 5 minutes break. Just 5 minutes, sir. It's only to refresh, because all this introduction I want to revise and start the real things. This is all introduction class, sir. Don't worry. Very slowly, gradually I will go. This is however introduction, sir. But I still want to revise this. So I'm taking only 5 minutes break. Everybody just take 5 minutes break and come. It is not a breakfast break. Today I'm not giving anything. Tomorrow onwards, we'll fix as every student requested, sir. Today you leave by 10. Tomorrow we will have the timings from 7 to 8:30 first session, 8:30 to 9 will be breakfast, and 9 to 10:30 will be second session. Okay, tomorrow onwards we will do that, sir. Today, because I did not inform, I will not give that, because 3 hours effectively according to me is good, sir. Okay, so just 5 minutes break I am taking. Yes, everybody. Everybody, please come back. So many still went. I want everyone to come back. Let us discuss what we started so far. Everybody come back. Still some students are missing. Okay, chalo, see, sir. Just review. This is introduction, sir. Don't worry, please. Don't worry. It's just introduction only, sir. There will be no break today. We will leave at 10:10, 10:15 maximum. But tomorrow onwards, I told Nasser, it will be from 7 to 10:30. In between, there will be half an hour break from 8:30 to 9. That's it. I told this anonymous attendee, I will block you because you are not giving your details. Reduce the speed. This is introduction class. I told there is nothing like speed. If you cannot understand, it is your problem. This is the normal speed I teach. Okay. And don't come here to by heart anything. So this is an introduction class which will be like this. Now one student is asking how many days it will take to complete. You want to decide or I want to decide? It depends. Already one student wrote how much speed. See, Mr. Mangesh, see one anonymous attendee wrote how much you are reduce the speed and you are asking how many days it will complete. So this is a problem. One student is feeling that I am speed, the other student say how many days. So it depends upon your capability. If your capability is low, it will never get completed. There is a problem. So don't ask such questions to please. Okay, don't ask such questions. You are having any plan or a meeting, you are any business meeting you are having. Mr. Mangesh, you are having any business meeting or you are very busy next month like me. I don't think so. So don't ask such questions. How many days it will complete? What is this? Don't ask such questions, please. No student dare to ask in our class also. Sunil, I am warning you. Sunil, I will remove you otherwise. How many days it will take? Okay. If video is not coming in laptop, it is your problem. Mahesh, please check it out. So one student is telling that already I'm sharing full screen. Okay, this is the correct screen I share. That is share, which is correct, which is D set. They are setting this perfectly. Chalo, everybody, now look here again. Now for precision, I'm closing my video because speed in my house with internet is really slow. So I have to compare. I have to compensate that. But still, doubt session we will take up at 10:10. 10:10, ask any doubt. I will talk, but not here. 10:10, you ask. Chalo. Everybody, yes, my subject, average marks in GATE 10. So range is from 8 to 12 minimum. Minimum is 8, maximum is 12. But 2 times in GATE 2012 and 17, it went even to 17 marks. Then in all other exams, I will say 10% of the marks come from my subject. IES mains, it is 84 out of 300 in conventional paper 1. But otherwise, GENCO, Transport, DISCOMs, Staff Selection Committee, ISRO, etc. Out of 100 questions, 10 questions are my subject, like 10%. Okay, in marks and division. Then I told how to get full marks in my subject. First, be perfect in our notes, sir. Okay, there is no secret. Okay. Be perfect in our notes. Read it 3 to 4 times. Okay, na? Then first do all IES objective papers first, because IES bits are without calculator, simple, fast, formula based. And GATE papers, do it later. Then lot of exams to practice. Okay, for conventional IES, of course, you read one textbook solved examples and also conventional paper solved. Okay, then there are a lot of exam papers. AS Academy will supply these books, but you have to purchase them. We have a lot of question banks, GENCO papers, Transco, ISRO, DRDO, so many civil services papers also we have. So please purchase them. because that is a secret to crack these exams. And then my textbooks are Alexander and Sadiku and Engineering Circuit Analysis. Both combination is ultimate. Okay, so if you clear prelims in IES, then take Alexander and Sadiku, do everything. All solved examples only. Only solved examples you do, plus read previous papers. Then you will get full marks in my subject. Then, sir, everybody, we have 3 parts in my subject. Part 1 is DC circuit analysis, which is 40%. Now, ideal DC steady state, dV by dt is 0 and di by dt is 0. Resistor behaves as a normal element, like DC voltage will give DC current, but inductor in steady state short circuit, capacitor in steady state open circuit. Then basics of time variance is chapter 4. There I will introduce how to analyze these inductors, capacitors for time varying signals. However, resistor is still homogeneous and proportional. Then we'll go to another 40% called AC steady state or sinusoidal circuit analysis, where resistor is still homogeneous proportional element, but inductor is a lagging element, where current lags voltage in a pure inductor by 90 degrees, and capacitor is a leading element, where current leads voltage, yes, by 90 degrees in phase. Then transient circuit analysis. This is about dynamic response. Okay, turning on, turning off, adding a load, removing a load. All such things come under dynamic solution to network, where stability of the networks will be considered. Then we have special topics like two-port networks, topology, locus diagram, dual duality, etc., which we will take care. Then what is the importance of electrical energy? Yes, electrical energy is superior because of many reasons, but the two outstanding reasons are interconvertibility and transportation. What is interconvertibility? Yes, we can convert different forms of energy into one common platform as electrical energy, and we can convert them back. That is a unique feature about this electrical energy, and no other energy has that advantage. Okay, so it is highly flexible in conversion. That is the reason today everything has become automation, and because of electrical science only. So in our house also, almost everything we are utilizing today is electrical energy only, sir. Electric cookers came, okay, electric ovens came. Even for cooking, we are depending upon electrical. Electric vehicles are coming already. Gas-based, we are now don't want petrol-based, we don't want pollution, at least at our place. Okay, we want to reduce it. So that is how electrical is number one. And the other reason is generation and transportation in bulk quantities, longer distances, and in the most economical way. Like even today, in most part of our country, with subsidized rates from the government, 1 unit of electrical energy, which is 1 kilowatt hour, is only 3 rupees, sir. Please understand that. Now we are learning this energy both at power level and signal level. Power level is high level, high voltage, high current, high power, but frequency in power system is constant 50. Signal level is low level, low voltage, low current, low power, but frequency in communication is kilo, mega, and gigahertz. At signal level, precision, accuracy, speed, controllability, and control intelligence are important. But at power level, we want efficiency, cost, power factor, voltage regulation, etc. So you buy air conditioner versus cell phone. Imagine like that. Air conditioner is a power level. There we look efficiency, power factor, etc. But mobile phone is a signal level where we want precision, accuracy, etc. Okay, there is a difference. Then how to learn this electrical science? Now I told here, yes, electrical science is not easy because our senses don't support. Then how to learn? We learn with notations and mathematics. Yes, we learn with notations and mathematics. What are notations? Like taking polarity for voltage and direction for current is also a notation. Like in a source, current leaves positive terminal of voltage, and in a sink, current enter positive terminal of voltage. Okay. For a source, power delivered is positive. For a sink, power absorbed is positive. Okay, that is the meaning of notation. Okay, now. Then another notation is about permanent magnet. Yes, another notation is about permanent magnet. Okay, now please understand permanent magnet. Yes, please understand what is permanent magnet there. Yes, we say flux leaves north pole externally, enters south pole externally, internally go from south to north. So that is another notation. That means taking flux direction is also notation. Taking polarity for voltage, direction for current is also a notation. Then another important rule, like example I'm giving, like Ampere right hand thumb rule. Okay, where thumb indicates current direction, closed fingers indicate orientation flux, and vice versa. Like that, we will learn Biot-Savart law, Lenz law, Faraday's law. Okay, and then Fleming left hand rule for motor, Fleming right hand rule for generator. Like that, sir. Everything is a notation. Now, sir, in electrical science, we cannot see and tell. So we follow these rules given by our great engineers, scientists, and ancestors. Then what is RLC? Why network theory is all about RLC? Yes, network theory is about modeling all our physical systems into such simple circuits using RLC components and analyze them for DC voltage, DC current, sinusoidal voltage, sinusoidal current, etc. But what they represent? Like resistor represents linear time invariant property of matter. Inductor represents electromagnetic property of matter, and capacitor represents electrostatic property of matter. Okay, now there is a meaning. Like example, you see here, capacitor notation. I took passive notation. Mathematically, we learn by Ohm's law. So, what is the Ohm's law for capacitor? I is C dV by dt. Now, with the help of Ohm's law, yes, with the help of Ohm's law, I teach now. Like for ideal DC, capacitor acts as open circuit in steady state, and ideal AC, capacitor is a leading element where current leads voltage by 90 degrees in phase. That is a mathematical I teach. But the science is different. That actually capacitor works with the principle of polarization. When polarities of voltage reverse, the orientation of flux reverse, and the charge accumulated in the plates also reverse. Okay, that is how the current in actual capacitor is called displacement current, but not the conventional current. So that is why, does really current flow through capacitor? Yes. No. My answer is no. And that current flowing through capacitor is called displacement current, where we will derive this in EMF. Okay, in EMF, your SAR will derive this, sir. Okay, but normal wires, etc., the current is called conventional current, where charge physically transfers there. Okay, that is the difference. So, conclusion is yes, engineering is application of science and analyzing by mathematical modeling. So, that is what I give the definition for engineering. Okay, so with all this introduction, everybody, yes, with all this introduction, now let us start the subject. Okay, now the first thing I want to differentiate is between circuit versus network. Okay, now I want to differentiate and learn everything. So the first thing I want to learn is about circuit versus network. Now onwards, everyone concentrate, sir. Listen carefully. Later you revise, listen to videos again and again. That is the best way. Chalo, now I am directly taking an example. Suppose this is 10 volts. 1 ohm, 2 ohm, 3 ohm. Now same thing I am writing here, but small modification. Everyone observe this. So this is 10 volt, 1 ohm, 2 ohm, 3 ohm, 4 ohm. Okay, see the difference, sir. Yes, circuit versus network. Now in a circuit, the most important property is here current I. Here current I is intended to flow. Okay, current I is intended to flow through all the components. Please understand, all the components. Okay, in a circuit, current I is intended to flow through all the components. But what are the conditions for current to flow? Yes, current requires two conditions. First, there should be a driving force. First, there should be a voltage or electromotive force, which is a driving force. And second requirement for current is there should be a closed path. Okay. Now see this very carefully. Everyone should listen now. Okay. Now, what is the difference between circuit and a network? See, circuits and networks are interconnection of various components to act together. Okay, everybody? Circuits and networks are interconnection of various components to act together. Yes, circuits and networks are interconnection of various components to act together. But in a circuit, current I is intended to flow through all the components. Okay, in a circuit, current I is intended to flow through all the components. Okay, but what are the conditions for current to flow? Two conditions. One, there should be a voltage or driving force, that is EMF, and there should be a closed path. For current to flow, yes, for current to flow, there should be a voltage or driving force, that is EMF, and there should be a closed path. And there should be what? Closed path. So this closed path concept is circuit. Now see here. See in this example, left example, there is a voltage and all are interconnected in closed path. Now total voltage by total resistance, total current will come. Okay, total voltage by total resistance, total current will come. It will again divide into two parts, current division, and current will come back. Whatever current leave the source has to come back, sir. Whatever current leave the source has to come back. That is law of conservation of charge. But here is current flowing through all the components? Yes. Yes, here current is flowing through all the components. Hence, it is a circuit. Now you see right side now. In the right side, there is no closed path for 4 ohms. See, current cannot flow through 4 ohm because this is open circuit. That means one condition is failed. The closed path concept has failed. So here there is open circuit, current cannot flow. So here current cannot flow through 4 ohms. Okay, na? Here current cannot flow through 4 ohms. Hence it is a network. That means in a network, yes, please understand. Hence, in a network, it is not mandatory. Okay, na? Hence, in a network, it is not mandatory that current should flow through all the components. Please understand this. Okay. Hence, in a network, it is not mandatory that current should flow through all the components. Understood what I'm trying to say? Yes, in a network, it is not mandatory that current should flow through all the components. Okay, but this network has a circuit in it. Now, please understand this. This network has a circuit in it. Now, this yellow color contour is circuit. This network has a circuit in it because that part is where current is flowing. But in a network, it is not mandatory that current should flow through all the components. In a circuit, it is mandatory that current is flowing through components. That means that part of a network where current is flowing is called circuit. Okay, that part of a network where current is flowing is called circuit. Okay, that part of a network where current is flowing is called circuit. Okay, please understand this. That part of a network where current is flowing is called circuit. Please understand this. That part of a network where current is flowing is called circuit. Okay, so circuits are building blocks of networks. Circuits are building blocks of networks. So here I will say, yes, here current is not here. Current is not flowing through. Yes, not flowing through. Okay, 4 ohm, as there is no closed path. As there is no closed path, hence it is a network. Okay, now give me the examples. Like your house is now network or circuit, everybody? Yes, your house, my house right now is a network only. Can you guarantee that all the components are turned on and everywhere current is flowing? No, na? Please understand this. Yes, current is not flowing through all the components because only that part which is turned on, current is flowing. So like that, in your house also, my house also, it is a very big network where all are connected but not turned on. But that part where current is flowing is called circuit. Okay, that part where current is flowing and energy is converting is called circuit. Otherwise, practical big systems are always networks. Now tell me your area and my area, like I stay in MIG colony, like you stay in Delhi or Gujarat, etc. Can you say it is a circuit or network? It is a big network because some areas power cut is there, some areas shops did not turn on. Okay, some business centers did not turn on. So that is how practical big networks. But that part where current is flowing is called circuit. Okay, practical big interconnected systems are always networks, but that part where current is flowing is called circuit. So I'm writing here, everybody listen. All our practical, okay, big interconnected, okay, interconnected systems, okay, all our practical big interconnected systems are networks, but we do circuit analysis. We do circuit analysis to those parts where current I is flowing. Okay, all our practical big interconnected systems are networks, but we do circuit analysis in those parts where current is flowing. Okay, all our practical big interconnected systems are networks, but we do circuit analysis in those parts where current is flowing. I will say circuits are building blocks of networks. Circuits are building blocks of networks. Example, our power system. Please understand it. Our power system is a big network. But a motor running in it is a circuit at power level. Circuit at power level, I will give power level. Okay, that is the meaning. So our power system is a big network. Okay, our power system is a big network, but a motor running in it is a circuit at power level. Another example, like our communication system. Our communication system is a big network. Okay, our communication system is a big network, but a transmitter, okay, a transmitter working in it, okay, working in it is a circuit at signal level, See this simple meaning. Everybody should read this page. Like all our practical big interconnected systems are networks, but we do circuit analysis in those parts where current is flowing. So that part of a network where current is flowing is a circuit. Circuits are building blocks of networks. Our power system is a big network, but motor running in it is a circuit at power level. Our communication system is a big network, but a transmitter working in it is a circuit at signal level. Okay. Now I will give a note. Saying that yes, EEE students or electrical engineering students learn power level. Okay. Power level. Okay. Closed path concepts. Okay. Closed path concepts, that is circuits. Closed path concepts like circuits. Like example, fault analysis. Okay. Fault analysis, power electronics. Okay. Fault analysis, power electronics, T&D, etc. Okay, everyone, see here, electrical people, we learn power level, that is circuit analysis, like fault analysis, power system, transmission and distribution, etc. But these ECE students, electronics and communication, they learn signal level. Okay, signal level. They do learn more network analysis, network concepts. They learn more about network concepts, which I will tell you, like Bluetooth. Okay, Bluetooth. Okay, Wi-Fi. Okay, Bluetooth, Wi-Fi. Okay, sonar, radar, mobile communication, etc. So please understand, like there is a difference. You see, this subject for electrical people is called, see this subject for electrical people is called as circuit theory. Okay, and this subject for EC people is called network analysis. You see this, sir. You see in your BTech, MTech, or everywhere, in any university or college or IIT. You see in any university or college or IIT, this is a basic difference. You see in any university, college, or even IIT, sir, there is a basic difference you will find. Like, see, for electrical people, this is called electrical circuit analysis, but EC people, it is called network theory. But what is the difference? I told, na, sir. See, I told the difference. Like electrical people, we are working at power level. Okay, electrical people, we are working at power level. For power level transmission, all closed path concepts, conductors are important, na? Yes, for electrical people at power level, all closed path concepts at power level are important, sir. All closed path concepts at power level are important. So that is why we learn circuit theory. Circuit theory, like you see now, you see circuit theory like fault analysis, power electronics, T&D, etc. But EC people, we learn at signal level. Signal level is low level. Okay, we learn network concepts more. Signal level is low level. We learn network concepts like Bluetooth, Wi-Fi, mobile. Because in ECE communication, we do transmit data, but not power level. Like your cell phone is there. You are calling to your friend. Your cell phone is transmitter. The other person receiving is also receiver. Both are independent circuits. But are they connected electrically? No. But signal is transmitting. So that is why two independent circuits we are communicating. That is why we call network concepts there, without any physical connection. That is why in your cell phone, yes, in your cell phone you say, array, in your cell phone network is there or circuit is there. We say network is there. Why? Because Airtel is a network, Vodafone is a network. Okay, please understand this. Airtel is a network, Vodafone is a network, Jio is a network. So electrical people at high power level, they study all closed path concepts where power is flowing, and that is circuit concepts. But EC people, at signal level. Without physical connection also, energy get transferred at signal level, and that is where network concepts they learn. Okay, they learn more what concepts? Network concepts. Please understand this. Okay, so that is why electrical people, fault analysis, power electronics, T&D is all circuit concepts. Bluetooth, Wi-Fi, mobile communication is network concepts. Okay, now I am giving the next definition. Everybody, yes, I am giving the second definition. That is network components. Listen now, network components or elements. Network components or elements. Network components or elements. Okay. Now, all our applications in electrical engineering, are our components. Okay, na? All our applications in electrical engineering, all our components. But when these, applications, okay, but when these applications are mathematically modeled, okay, mathematically modeled as circuit or network, okay, na? But when these applications are mathematically modeled as a circuit or network, we use fundamental network components, okay, such as B, I, R, L, C, etc. to model them. Listen to this, sir. Please listen to this. I will explain again. Everybody listen. See, all our applications in electrical engineering are our components. Okay, na? But when these applications are mathematically modeled as a circuit or network, we use fundamental network components such as voltage source, current source, resistor, inductor, capacitor, etc. to model them. Okay, later diodes, transistors, thyristors, also we will use transformers, etc. But that is the meaning. So all our applications in electrical engineering are our components. But when these applications are mathematically modeled as a circuit or network, we use fundamental network components to model them. I will give an example. Example 1. See, I want to learn about a heater. Everybody, I want to learn about heater. Heater is an electrical application which converts electrical to heat, sir. Yes, heater is an electrical application which converts electrical to heat. Okay, na? So heater is an electrical application which converts electrical to heat. But if I want to teach about heater, now tell me, out of all this VIRLC, which component can model heater? Because heater will convert electrical to heat and only resistor can model it. Na? So that is why finally in my electrical engineering subject, I model heater as a resistor. Now I will apply Ohm's law, where this is the voltage given and current flowing based on Ohm's law. Then power absorbed by the heater, either I can do I square R or V square by R, or simply V into I watts. Yes or no, like that. So if it is DC voltage, I will take DC currents, but if it is an AC voltage, I will take RMS values. Which I will tell you why. Okay. So heater is an application which converts electrical to heat energy. But if I want to understand heater mathematically, I should model it first. Yes, if I want to understand heater, I should model it first. So I will model heater as a resistor. Okay. And then power absorbed by the heater is I square R or V square by R or V into I. Like that we learn. Another example. Example 2 is about a fan, ceiling fan, which is our single phase induction motor. A fan is an example of single phase induction motor. Now fan converts what energy to what energy? Electrical to mechanical. Okay. Fan converts electrical to mechanical. Yes or no? Yes, fan converts electrical to mechanical. That is true. Yes or no, sir? Yes, fan converts electrical to mechanical. But if I want to learn, about fan and its principle of operation, performance, etc., I should model it now mathematically. Yes, I should build the equivalent circuit. Now, single phase induction motors have equivalent circuit. Like this fan has main winding. Yes, it has got main winding. Then it has got auxiliary winding. Okay, it has got auxiliary winding.
It has a capacitor to start. Okay, and there is a centrifugal switch. Now this fan has a rotor inside. Yes or no rotor, which is short-circuited rotor bar. This is a short-circuited rotor bar. Okay, so and this practical winding has inductance and resistance. Here also inductance, resistance, capacitor to start, and this is a switch, centrifugal switch, and this is a rotor. But this fan is an AC machine, sir. So AC machine. So I will give sinusoidal voltage. Okay. Yes, I will give sinusoidal voltage. Current is also sinusoidal accordingly. Okay. So that is how. Though fan is an electrical machine which converts electrical to mechanical, but to understand fan, I need its mathematical model. And that is where network theory is automatically coming. You see that. Now you see this definition. All our applications like heaters, motors, etc. are our components. But when these applications are mathematically modeled as a circuit or network, okay. But when these applications are mathematically modeled as a circuit or network, yes, we use fundamental network components such as VIRLC to model them. Okay, na? We use fundamental network components such as VIRLC, etc. to model them. Okay, that is the meaning. Now you see this like a heater, I'll model in terms of register. Okay, na? That is the meaning. Then fan is an induction motor which converts electrical to mechanical. Fan is an electrical machine which converts electrical to mechanical. Okay, yes, but I will model it as an RLC circuit. Similarly, example 3 I will give. Now I want to teach about BJT. What is BJT? BJT is a bipolar junction transistor. It has got a lot of applications like amplifier, oscillator, etc. So no, but to understand all BJT circuits, I need its equivalent circuit now, mathematical circuit, that is H parameter equivalent V1. And this thing we learn in analog na, sir. So there also network theory is coming. So yes, this BJT is a bipolar junction transistor. It is a device. But this device has a network model using H parameter. So we model this like this because BJT is a current dependent current source. We model something approximately. I'm writing, sir. Approximate models. Okay, we model something like this. Like this is base, collector, and emitter. Base, collector, emitter. Like this is base resistance. This is beta IB, which is IB. Okay, and this is something like VCE. Okay, approximate, sir. I may not be accurate, but concept I want to teach. That means even a BJT, which is a device, which is a semiconductor device, but to learn anything about BJT and its applications, I need to mathematically model it, na, sir. Yes, I need to mathematically model it. Yes or no? Yes, I need to mathematically model it. Okay. Yes, I need to mathematically model it, and that is where. Yes, even a BJT has a network model. Okay, na? Even a BJT has what model, sir? It has what a network model. That is the meaning here. Even BJT has a network model. Okay, na? That is the meaning of it. Okay. So now in this regard, yes, I am going to next definition. That is linear components. Everybody listen. Linear components or linear elements. Linear components or linear elements from which we get linear networks. If all the components are linear or all the elements are linear, we get linear networks. Now, what is the meaning of this? Now, listen carefully, sir. All our practical components, are originally non-linear in nature. Okay, all our practical components are originally non-linear in nature, but any non-linear network or system, any non-linear network or system can be linearized for small incremental changes in time. Okay, all our practical components are originally non-linear, but any non-linear network or system can be linearized for small incremental changes in time. But the same network or system Yes, but the same network or system for sudden big changes, big changes, big changes undergoes non-linear mode of operation. Non-linear mode of operation. I will tell you, sir, listen carefully. Don't worry. See, these are all basics. That is why here I am going with basic things, simple way and easy way. When we come to the real things and applications, there I will teach again and again repeatedly, neatly. So what is the meaning of linear components or linear circuits? That is why you see so many textbooks are written as linear network analysis, linear circuit theory, like that they will write. Okay, they will write like linear network analysis, linear circuit theory, like that they will write. Okay, what does it mean? What does it mean? Okay, so all our practical components are originally non-linear in nature, but any non-linear network or system can be linearized for small incremental changes in time. But the same network or system for big sudden changes undergoes non-linear mode of operation. Now, what is the meaning, sir? What is the meaning? Let us understand this. Okay, what is the meaning? Suppose I write two functions. Please understand. I am writing two functions. Function f1 in time and function f2 in time. Function f2 in time. Okay. Now here I wrote one function like this. Now here I am writing a function like this. Something like this. Now you tell me out of these two which is linear and which is non-linear. You tell me now which is linear and which is non-linear. Yes, you tell me now. See, the first one is linear. Why it is linear? Because it is obeying proportionality. Homogeneous means it is obeying the principle of proportionality. Please understand this. Homogeneous. And we can model mathematically. So this equation is like a ramp function like y equal to mx. Yes or no? So this can be modeled. Yes, this can be modeled accurately in max. Okay, this can be modeled accurately in max. Okay, that is why I say it is a linear function. Why? Because it is obeying the principle of homogeneity or proportionality, and it can be modeled accurately in max. Like suppose if it is a voltage versus time, I say it is a ramp voltage. But right side is a non-linear. Right side is non-linear. Why? Because here homogeneity is failed. Initially increasing, suddenly decreasing, again increasing, and there is no uniform periodicity. Now here after this, can you say increasing or decreasing? You cannot say. But here you can predict. Left side, it is proportionally increasing always with time. But here you cannot predict. So it is non-homogeneous. Okay, non-homogeneous. So it fails Ohm's law. And you cannot model. Accurately in max. Cannot model this function. Okay, this function accurately in max. Okay, you cannot model this function accurately in max. So please see the difference. One way, left side is a linear function. This is a linear function. This is a non-linear function. What is the basic difference? The basic difference is in linear functions, it obeys homogeneity or proportionality, and it can be modeled mathematically very accurate. But in the right side, they are non-homogeneous and you cannot model it accurately. But I told a statement here. Though all our components and systems are originally non-linear, but any non-linear system can be linearized. See this. But any non-linear system can be linearized for small incremental changes in time. But the same system for sudden big changes undergoes non-linear mode of operation. Now let us understand the mathematical meaning. So, though everything in the world is originally non-linear, how to make it linear? Now that is where engineering concepts are coming. See, suppose I take a non-linear function 2 times I am taking. Okay, this is function f of x, where x is the independent parameter. I am taking this function 2 times. I'm taking this function 2 times. F of x, x. Now here, I am writing this function 2 times. Okay. Yes, it is a non-linear function. Okay. Now here, first I will consider small incremental change in x. So this delta x is small. Okay, this delta x is small. or incremental incremental. Okay, this delta x is small or incremental. Now for this small change, if I use a straight line and join these 2 points, yes, please observe, if I use a straight line and join these 2 points, now the original green curve, which is non-linear, but this white line has become linear in this small range. Though originally our function is non-linear, which is green line, but for small incremental change, I can model this as a white line, which is linear now, like y equal to mx plus c. So here I can say the actual line has been approximated as linear, in this small range or incremental range. But the same function, suppose I consider this delta x as big or sudden. But the same function, if I consider this delta x as a big or sudden, delta x is big or sudden. Yes, delta x is big or sudden. And if I join this with straight line, yes, if I join this with straight line, okay, now this is my actual function. This is my actual function, and this is my approximate function. Yes, this is my actual function. So here they are not correct in mathematical modeling. So what is the difference? See, originally this green line is a non-linear. Why it is non-linear? See, increasing and then saturation decreasing. So homogeneity failed. So originally the green line function is a non-linear function. But this function for small incremental change where delta x is small, I can model it as a linear function. But the same function for large delta x sudden change, it cannot be modeled accurately. So that means that is the statement. Now listen to this. See, after looking this example, now read this statement. So all our practical components or networks are originally non-linear in nature, but any non-linear network or system can be linearized for small incremental changes in time. But the same network or system for big sudden changes, yes, for same network or system for big sudden changes undergoes non-linear mode of operation. Undergoes what? Non-linear mode of operation. Now what does it mean? Now I can say, yes, here I can say, yes, though originally everything in the world is non-linear, for small incremental changes, I can model it linear. For big sudden changes, it is non-linear. So that is why every electrical network, every electrical component, yes, component or network, understand this, every electrical component or network, okay, component or network has ratings or specifications. Okay, has ratings or specifications. Okay, every electrical component or network has ratings or specifications. Every electrical component or network has ratings or specifications. Okay, so if you operate and design them within the ratings, they are said to be linear, sir. If you operate and design them within the ratings, yes, you can say like this. If you design and operate them within the ratings, they are said to be linear. But if you go beyond the ratings, they are non-linear. That is the meaning. For small incremental changes, they are linear. For big sudden changes, they are non-linear. Now, best example I am giving here. Everybody listen to this. Okay, now best example I am giving everybody. See this here. The best example is, yes, example of a diode. Listen carefully. Example of a diode. Now, originally diode is linear or non-linear? Yes, originally diode is absolutely non-linear, sir. Because you see the characteristics of diode. Forward characteristics of diode if you plot. Okay, diode voltage versus diode current. I will go ulta. Okay, this is diode current and this is diode voltage. Okay, suppose you plot this now, sir. Original characteristics, how they come like this now. Yes, original characteristics of diode is like this. It is an exponential function. You know, na, sir, I naught is equal to, yeah, I into e power eta vt minus 1 like that. So originally it is a non-linear function. So originally diode is non-linear. Then how to understand diode if it is non-linear? How we are able to do circuit analysis? Though originally diode is non-linear, but we do operate in its range. Like as a clipper or clamper, I will operate diode in its range. As a clipper or clamper, I will operate diode in its range. Okay, I will operate diodes in its range. Okay, in this range, it is a straight line. In this range, it is a straight line. Okay, here I can model it as a small signal. Yes, here I can model it as a small signal analysis of a diode. Analysis of diode. What is the same definition? Though originally diode is non-linear, for the small rated values within the ratings, incremental change. See, that is the meaning. for small incremental change, that is called small signal analysis of diode. This original diode, which is non-linear, I can model it as a linear component like resistance and cutting voltage. So though diode is originally non-linear, but we can model it as a linear component. Though diode is originally non-linear, we can model it as a linear component. There is a meaning, sir. There is a meaning. See, this green line characteristics is exponential function. It is non-linear because homogeneity failed, proportionality failed. But though it is non-linear, I will operate within the ratings. Then it is said to be linear. That is why small signal analysis of diode, small signal analysis of transistors, these are all called what concepts? Linear concepts. Though diode is non-linear, but we operate them within the ratings is said to be what? Linear. Now I'm giving this note. Everybody understand this note is important, that in electrical circuit analysis, yes, in electrical circuit analysis, if every component, okay, is designed and operated okay, within the ratings, okay, is said to be linear. Okay, if every component is designed and operated within the ratings, is said to be linear, where it obeys Ohm's law, Kirchhoff's laws, KVL, KCL, etc. That is the meaning, sir, finally. So obeying Ohm's law itself is homogeneity. Okay, now obeying Ohm's law itself is obeying homogeneity. That is a big observation. So everyone, I am repeating again, sir. Big definition we have learned. What is the meaning of linear components or linear networks? Everybody listen again. This is introduction class. This is not speed. My wording, see, my English is like this, sir. But this is not speed. And these are all basic definitions. I will slow down when required. See, after this, all notations, definitions. See, definitions also, if I teach very slow, na, sir, you cannot complete syllabus even in 1 month. That is why these are definitions. Definitions I'm going, see, in this online, na, sir, we are not able to dictate, na, sir, we have to write. That is why you are feeling like that. But once we overcome this, then it is easy. First definitions, formulas, notations. First I told Nasar 6 to 8 hours it will be like this. But after that you will enjoy. So everyone have some patience. First to 6 to 8 hours I need to complete these definitions, sir. Otherwise definitions also, if I don't write and tell, you will not understand. And moreover, if I waste time here, this is a very, very big subject, I'm telling you. Very biggest subject. It has got so many chapters other than other subjects. Okay. So please understand this. Okay. So linearity means obeying Ohm's law. Not VI is linear. Yes, I will explain again. Chalo, now listen. What are the meaning of linear components or linear networks? Now, though our practical components and networks are non-linear, but any non-linear component or network can be linearized for small incremental changes in time. That is why if you design and operate them within the ratings, they are said to be linear, sir. But the same system for big sudden change is a non-linear mode of operation. So suddenly, if you go beyond the ratings, they are non-linear. Like example, left side is linear, right side is non-linear. Okay. Now, though everything is non-linear, but the same non-linear for small incremental change is linear, but fixed sudden change is not modeled as linear. Now, what is the example? Though diode is originally non-linear, but we operate them within the ratings, like as a clipper or a clamper within the operating point, and there it is acting like a linear component. There it is acting like a linear component. Hence, diode can be modeled as a linear network. So in electrical circuit analysis, if every component, yes, is designed and operated within the ratings, it is said to be linear. Then it obeys Ohm's law, Kirchhoff's laws, etc. That is the meaning, sir. Okay. Then another important classification is unilateral versus bilateral. First, bilateral component. What is bilateral component? Now the example for bilateral component is resistor. Why resistor is bilateral? Let us see this. Suppose you take a 2 ohm resistor. Okay, 2 ohm resistor, and I am taking current from left to right. Let us assume there is a closed path. Let us assume there is a closed path and current is going from left to right. What is a passive element? In a passive element, the direction in which current enter is taken as positive. The direction in which current enter is taken as positive. So 3 2s are 6 volts. 3 2s are 6 volts. Okay. Now your power absorbed is how much? Either I square R or V square by R or V into I. 18 watts. 18 watts. Okay, na? Yes. It is I square R or V square by R, V into I, 18 watts. Now the same component. Okay, now let us consider the current is going from right to left. Let us consider the current is going from right to left. And if current is entering right, passive notation, again, this is plus, this is minus, 3 2s are 6 volts. 3 2s are 6 volts. Again, power absorbed is how much? Again, power absorbed is how much? 18 watts. Again, power absorbed is 18 watts. Okay, now I am giving this definition that, yes, the properties or characteristics, okay, the properties or characteristics of such components, please understand this, okay, the properties or characteristics of such components, okay, are independent to, yes, independent to circuit condition, okay. Example, RLC are bilateral components. Please understand this. Everybody should understand this. See, bilateral component. Resistor is the best example of bilateral. Why? See, in this component, you see whether current is going left or voltage polarity left is positive, or current is going right, voltage polarity right positive. The behavior of this component is not changing. Okay, now the behavior of this component is not changing. So the properties and characteristics of such components are independent to circuit condition. Whether current go right, left, up, down, the properties will never change. Such components are called what? Yes, such components are called bilateral components. RLC network, RLC elements are bilateral. Okay. Now what are unilateral components? Unilateral components. Now the best example here is diode. Okay. Now you see this. Now suppose I take a diode and I give this polarity. Now for this polarity, diode is forward biased. Okay, and it will conduct as a closed switch. It will conduct. Yes or no? It will conduct. And the on-state resistance of diode is how much? 0. The on-state resistance of diode is 0. Now the same diode, I give ulta polarity. Now this is reverse biased. Will not conduct. Okay, will not conduct. Then the off-state resistance of diode is infinity. Off-state resistance of diode is infinity. Now see the difference in this component, sir. See, in this component, in one case, the polarity comes left positive, right positive, that is anode positive with respect to cathode. It is forward bias, it will conduct, and on-state resistance is 0. But in the right case, yes, cathode is positive with respect to anode. It is reverse bias and it will not conduct. Off-state resistance is infinite, like open circuit. So clearly the properties of such components, so I'm writing the properties or characteristics. The properties or characteristics of such components, okay, the properties or characteristics of such components depends upon circuit condition, Please understand this. Okay, the properties or characteristics of such components depends upon circuit condition. So all examples like diodes, okay, BJTs, thyristor SCR, etc. are all unilateral. Okay, please understand the difference. So the properties and characteristics of such components do depend upon circuit conditions, whether forward bias or reverse bias, etc. So I gave the theoretical definition. In resistor, inductor, capacitor, generally in sir, the properties of such components are independent of circuit condition. But in diodes, transistors, MOSFETs, BJTs, and SCRs, the property depends upon circuit condition. Now, mathematical definition. Now, based on static VI characteristics. Okay, VI characteristics. Okay, based on static VI characteristics, I can also say like this. So if I take this VI characteristics, which has Ohm's law characteristics, voltage as x-axis, current as y-axis. Now I will apply that. Now if the component characteristics in first quadrant and third quadrant are symmetrical, in first quadrant and third quadrant are symmetrical. Now this is the meaning. If characteristics in first quadrant is equal to third quadrant, which are symmetrical, okay, which are symmetrical, then the component is bilateral. But if first quadrant characteristics is not equal to third quadrant characteristics, that is asymmetrical, then it is unilateral. Asymmetrical, then it is unilateral. So please understand what I'm trying to say. If the first quadrant and third quadrant characteristics are symmetrical, then the component is bilateral. But if first quadrant is not equal to third quadrant, if the first quadrant is not equal to third quadrant, it is asymmetrical, then it is unilateral. Symmetry is a bilateral property. Now, what does it mean? Mirror image you have to see, sir. Symmetry is a mirror image. That means if the characteristics of any component, in the first quadrant and third quadrants are mirror image, then they are bilateral. But if the characteristics in first quadrant and third quadrants are asymmetrical, then it is a unilateral. Okay, then it is unilateral. Okay, now in that regard, yes, everybody in that regard. Now let us apply this to our examples. Let us see. Chalo, our examples, what we took, we took one resistor and we took one diode. You remember, we took one resistor and we took one diode. Suppose let us take our examples. In our example, first resistance of 2 ohms I took. Now in resistance of 2 ohms, if I plot the Ohm's law, voltage versus current, if I plot the Ohm's law, everybody listen now. Now, if I give 6 volts, yes, if I give 6 volts, 3 amps is flowing. This is the operating point. Suppose if I give positive 12 volts, 6 amperes will flow, and this is the operating point. Yes or no, like that, this is the operating point. Similarly, reverse side, if I give minus 6 volts, see what is the meaning of minus? Ulta polarity. Okay, like ulta, with respect to this is called minus. With respect to left one, I say right side is minus. So here, if I give minus 6 volts, current also will reverse minus 3, and this is the operating point. And if I give minus 12 volts in the reverse side, current also will reverse, and this is the operating point. Now if I join all these operating points, now listen carefully. Yes, if I join all these operating points, now watch this. Yes, I would say the first quadrant and third quadrant characteristics are symmetrical. Here first quadrant is equal to third quadrant. It is symmetrical mirror image, hence it is a bilateral element. Hence it is what? Bilateral element. But same example, let us take diode example. Now diode characteristics we already know, sir. We already know diode characteristics. Yes, we already know diode characteristics. Okay, voltage across diode, current through diode, negative voltage across diode, negative current through diode. Now there, if you see, forward bias characteristics are like this. Reverse bias, it will block, only leakage currents will flow. But if you exceed reverse break or voltage, it will break down also. Now here clearly, if you observe, sir, this first quadrant and third quadrant are not equal, asymmetrical. Yes, here first quadrant is not equal to third quadrant. It is clearly unilateral, asymmetrical, unilateral component. Here clearly the first quadrant and third quadrants are asymmetrical, unilateral. Here first quadrant is not equal to third quadrant. It is asymmetrical, unilateral. Please understand. Asymmetrical, unilateral. So that means, see this definition now. So if first quadrant and third quadrants are symmetrical, bilateral, they are mirror image. But if they are not mirror image, asymmetrical, unilateral. So same meaning, here you see in register, this first and third are mirror image, symmetrical, so they are bilateral components. Here first and third are not mirror image, asymmetrical, unilateral. Okay, that is the meaning. Now I'm asking a question here. Everybody, question to you. Tell me about SCR and tell me about TRIAC. Tell me about SCR and tell me about TRIAC. I'm giving only 1 minute. Okay, tell me about SCR and tell me about TRIAC. Tell me about SCR and tell me about TRIAC. Everybody should try to answer this. Tell me about SCR and tell me about TRIAC. Okay, tell me about SCR and tell me about TRIAC. Some students already are telling, very good, sir. Okay, don't worry. Your answer may be correct or wrong. I don't mind that. But your attempting is important. Chalo. Yes, everybody. In SCR, if I plot the characteristics, everybody plot. See this. SCR is a silicon control rectifier. It is one of the main member of the thyristor family. Okay, like voltage, current, negative voltage, negative current. Now, SCR is a gate trigger device. So if you give gate pulse current, it will work. Okay, now if I observe carefully, yes. So if you exceed the breakover voltage, it may work, but that is dangerous. Okay, but we give gate pulse triggering for low voltages across the anode. That is the meaning. And reverse bias, it will block. And if you exceed the reverse breakover voltage, it will trigger. So here clearly, the first quadrant and third quadrant characteristics are asymmetrical. Here first quadrant is not equal to third quadrant, asymmetrical. First quadrant not equal to third quadrant. So it is a unilateral switch. That is why SCR can work only in one direction. It is preferred for rectifiers where supply is AC to DC because it is only doing DC switch. It is a DC switch. It is like a DC switch, I say. DC switch, simple DC switch because it will control only in one direction. Output voltage and output current can be in one direction. It will block two voltages, but current is only in one direction. Okay, better preferred for rectifiers, control rectifiers. But TRIAC, you see, sir, TRIAC is also a member of the thyristor family, but it is a low power or medium power range device. So if you plot the TRIAC characteristics, this is also very interesting. It is also gate triggering device. If you exceed the forward breakover, you can give, but for low voltages, you give gate pulse, it will trigger. Okay, it will trigger. For low voltages, it will trigger. Similarly, this side also, if you observe, yes, this side also, if you observe, yes, if you give this, okay, for low voltages, it will trigger. So that means here, if you observe carefully, the first quadrant, yes, if you observe carefully, the first quadrant and third quadrant are mirror images. Here, first quadrant is equal to third quadrant, mirror image. It's a bilateral switch. Bilateral switch. It's a bilateral switch. Okay, that is AC switch. That is why TRIAC is a AC switch. AC switch. TRIAC is a AC switch. Okay, TRIAC is a AC switch. Please understand this. Okay, so SCR is a unidirectional switch or unilateral switch. TRIAC is a bilateral switch. Why? TRIAC can block both voltages and also conduct both voltages, both sides. TRIAC can block both voltage polarities and conduct both current directions. So it is an AC switch. That is why we use it as AC voltage controller directly. But SCR can block both voltage polarities but can conduct only in one direction. It is a DC switch. So SCR's property in both sides is not same, but TRIAC's property in both sides is same. That is why TRIAC is a bilateral switch, but SCR is a unilateral switch. That is the meaning, sir. That is the real meaning of such a classification. Okay, now. Similarly, that means in my subject, you see now, in my subject, mostly we deal with bilateral components. That you remember, sir. See, circuit theory is mostly RLC components now. So we deal with the bilateral components. But analog electronics, power electronics, they deal with the unilateral components like thyristor, transistor, diodes, etc. So ideal circuit theory, my subject is mostly bilateral elements like RLC, but your analog, okay, power electronics, etc., they deal with the unilateral elements also. That you remember. Okay, now. So now next definition about active and passive element. Active elements or source. Okay, now active elements or sources. Okay, if any element, okay, if any element can, okay, if any element, okay, can generate, okay, generate or give out or drive out or energize, okay, or deliver. I also give this classical meaning, deliver. Okay, if any element can generate, give out, drive, energize or deliver, yes, deliver externally electrical energy, then they are said to be sources. Example, voltage and currents are ideally sources. Now for a source, what is the notation? For source, what is the notation? In any element, yes, if current leaves the positive terminal of voltage, okay, it is called as a source. It is called as a source. Now in a source, power delivered is positive V into I watts. But in a source, if someone say what is the power absorbed, that is a wrong question. You have to say negative VI watts. I will tell again, sir. Everyone listen. Okay, I'm explaining again. Everyone should listen, please. Now we are learning another definition called source and sink. Okay, we are learning another definition called source and sink. So what are sources? If any element can generate, give out, drive, or energize. Okay, if any element can generate, give out, drive, or energize externally with electrical energy, they are called sources. Generally, voltage and currents elements are sources. What is the notation? In any element, if current leaves the positive terminal of voltage. In any element, if current leaves the positive terminal of voltage, then it is called source. For a source, power delivered is positive, correct? Because source delivers, sir. For a source, power delivered is positive. But if someone asks what is the power absorbed, if someone asks what is the power absorbed by the source, that is the wrong notation. Source cannot absorb power. What is the power absorbed? That is the wrong. Source will deliver, na sir. How can it absorb? So power absorbed is negative VI watts. Okay. And power absorbed is negative VI watts. Okay. Power delivered is positive. Power absorbed is meaningless, na sir. So you write negative. Then what are passive elements or sinks? Yes, passive elements, which are also called sinks. Passive elements or sinks. Okay, if any element, yes, if any element, okay, absorb, okay, absorb, store, dissipate. I also use convert, okay, or waste, okay, electrical energy in any form, okay, then that's said to be sinks. Generally, RLC components are globally sinks, where we know that resistor will dissipate electrical energy in the form of heat. Okay, electrical energy in the form of heat. Okay, inductor will store electrical energy in electromagnetic flux. Okay, or electromagnetic form, that is electromagnetic flux. Capacitor will store electrical energy in electrostatic charge. Okay, now what are passive elements or sinks? Yes, if any element absorb, store, dissipate, or convert or waste electrical energy in any form, they are said to be sinks. Generally, RLC components are sinks. Okay, now generally RLC components are sinks. Okay, yes, generally RLC components are sink. Now, resistor will dissipate or convert energy in the form of heat. Inductor store energy in electromagnetic form flux. Capacitor can store energy in electrostatic form charge. Now, again, notation is important. Okay, Okay, we should be interested in notation. Now, what is the notation here? Yes, the notation is in any element. If current enters the positive terminal of that element, then it is a sink. Yes, in any element, if current enters the positive terminal of that element, it is a sink. Now, in a sink, power absorbed is positive VI watts. Correct. Sink power absorbed is positive. Power delivered is negative VI watts. So, if someone asks what is the power absorbed, yes, power absorbed is positive. In a sink, power absorbed is positive. That is true. Power absorbed is positive because sink absorbs. But if someone asks an ulta definition, what is the power delivered? There is a wrong meaning, sir. How can sink deliver? It is wrong meaning. So you have to put negotiate. You have to mathematically argue it is ulta. So in a source, power delivered is positive, power absorbed is negative. But in a sink, power absorbed is positive, power delivered is negative. Now again, mathematical definition. Now based on static VI characteristic. Okay, based on static VI, steady state. Static means steady state characteristics. Now this is again important. Like in our Ohm's law plane, which is our voltage current quadrant. Now we dedicate first quadrant and third quadrant for sinks. First quadrant and third quadrant belong to sinks. However, second quadrant and fourth quadrant belong to source. Okay, first quadrant and third quadrant belong to sink, and second quadrant and fourth quadrant belong to source. Please understand the meaning. Okay, first quadrant and third quadrant belong to sinks, and second quadrant and fourth quadrant belong to source. That is our notation, sir. We are giving these notations. I will give an example. The best way to understand is by an example. Chalo, example is example of a rechargeable battery. Rechargeable battery. Okay, now the best example is a rechargeable battery. Now here, most of our cell phone batteries are rechargeable, na sir? Yes, rechargeable. Okay, now what happens there? Charging and discharging. Now see the meaning. I will explain this concept of notation in this example. Now, right now, our cell phones batteries are discharging. Discharging means they are acting like source. The batteries are acting like source because they are driving the screen, driving the speaker, etc. So most of our cell phone battery voltage is 3.7 volts. That is almost constant always. But right now, what they are doing? They are discharging. Discharging means yes, they are discharging. So it is in the discharging mode. It is which mode? Discharging. So it is a source mode. So I represent them in which quadrant? Fourth quadrant. Source mode. Discharging source mode. But the same battery. Okay. If I connect it to charger, but the same battery if I connect it to the charger. Okay. But the same battery if I connect it to the charger. Okay. Yes, the same battery if I connect it to the charger, what happens now? The current will reverse. It is in charging mode. Charging mode. It is so sync mode. So when you connect your battery to the charger, the battery is getting charged now. Yes. When you connect that to the charger, it is in charging mode. That time it is a sync. Okay, that time it is a sync. So that means your cell phone battery is the best example to understand these two quadrants. When it is discharging normally, that time source, it is acting like a source, battery is discharging, converting chemical to electrical. I will represent them in which quadrant? Fourth quadrant, source mode. But voltage is almost constant. But when you connect back to the charger will drive current energy or current through the battery from positive to negative. Current will reverse. That is why current I am showing reverse direction. But voltage is almost same, neglecting voltage regulation. And this is a charging mode, which is a sync mode. So that is why first quadrant belong to sync and fourth quadrant belong to source. Voltage is almost constant. Now you may say, sir, but why are you showing different current levels? Now concept, see how much current in the battery will depend upon the applications you run. In discharging mode, how much current depends upon the applications you run. Suppose you are using battery only to speak, standby mode, very less current it will draw, or less current is flown out. But you are playing video games, audio, speaker, then huge current it will draw. So how much current while discharging depends upon application. Similarly, how much current while charging depends upon the charging technology. Normal charging is slow charging, very slow current will flow. But today all dash charge technologies came, dash charge, fast charging. So huge current will flow. So a cell phone battery is the best example of understanding these quadrants. Another example I need. See, another example is, another example of a synchronous machine. Synchronous machine power circuit diagram. Now in synchronous machine, see sir, in our Bimbra book, Teresa, they give this power circuit diagrams like this. Okay, in a synchronous machine, they give like this. Now in this first quadrant, the synchronous machine acts as a synchronous motor. It is acting like a sink. Okay, synchronous motor, it is acting like a sink where it converts electrical to mechanical. But the same synchronous machine in second quadrant acts as synchronous generator. It is acting like a source. So the same synchronous machine in first quadrant acts like synchronous motor. Okay, it acts like synchronous motor. Okay, and the same synchronous machine in please understand, in synchronous machine in second quadrant is like a synchronous generator, acts like a source. So again, you see first quadrant sink, second quadrant source, that concept. Okay, such things we learn, sir. In machines we learn this. Okay, now. So we classified now elements into three types, sir. Everybody. Okay, we classified elements into three types. Everybody should listen now. Okay, first we classified into linear and non-linear. Okay, yes, everyone please listen. We classified first elements into linear and non-linear. Okay, then unilateral and bilateral, unilateral and bilateral, then passive and active, active, okay, and passive, and how to represent also we give. Okay, examples also I give. So now I am asking this gate question. Gate question, everybody. Okay, the static VI characteristics of a particular component is shown below. Okay, the static VI characteristics of a particular component is shown below. Then component is dash. Component is dash. The static VI characteristics of a particular component is shown below. Then the component is dash. Now I'm giving options: linear, active, bilateral, linear, passive, bilateral, non-linear, active, unilateral, non-linear, passive, bilateral. So everybody tick the correct option and keep quiet. See, I'm giving that the static VI characteristics of a particular component are shown below. Okay, the static VI characteristics of a particular component are shown below. Then the component is dash. I give some options. Okay, the static VI characteristics of component. The static VI characteristics or steady state VI characteristics of a particular component are shown below. Then the component is dash. Linear active bilateral, linear passive bilateral, non-linear active unilateral, non-linear passive bilateral. Yes, I'm giving the answer. Yes, so many are giving very good, sir. Yes, very good. See now, listen. See this component until here is obeying Ohm's law. Because voltage is increasing, current is proportionally increasing. Here also voltage is decreasing, current is proportionally decreasing. But after this point, what happened, sir? Even though the voltage is increasing, current is constant. Even though the voltage is increasing, current is constant. Saturation. Saturation is a non-linear property. This side also, though voltage is increasing or decreasing in negative side, current has stopped. Current is constant. Saturation. So overall, it is non-linear. Overall, non-linear because Ohm's law failed. Na? In this small range, it is linear. But after this, voltage is increasing, but current is constant. Here also, voltage is decreasing, but current is constant. So overall, non-linear. In this small region, it may be linear, but overall, non-linear. It is overall non-linear. Okay, na? Then first and third quadrant. First and third quadrant is passive or active? Passive. First and third quadrant is passive. Okay, please understand. First and third quadrant is passive. Then unilateral, bilateral, unilateral, bilateral, bilateral, bilateral. Okay, because mirror image symmetry. So Ohm's law is failed. Non-linear. First and third quadrant passive, and mirror image bilateral. So non-linear, passive, bilateral, non-linear, passive, bilateral. Okay, now that is the meaning there. Please understand. So now I am giving another question. This is IES question. Same meaning, sir. The static VI characteristics of a particular component are shown as below. The static VI characteristics of a particular component are shown as below. Then the component is dash. Okay, the static VI characteristics of a particular component are shown as below. Then the component is dash. Okay, chalo, now write the answer, everybody. The static VI characteristics of a particular component are shown as below. Then the component is dash. Everyone should write the answer. Just 1 minute, everyone should write the answer. Okay, everybody. Yes, answers. Very good, sir. Some students are writing. I'm happy, sir. Now see, this is again non-linear because homogeneity fail. It is a parabolic, na, sir. Like if you double the voltage, current is doubling. No, if you double the voltage, current is increasing square times. So it is non-homogeneous. So non-linear. It is non-linear. Correct. It is non-linear. Actually, this is both passive and active. Both passive and active because first quadrant is passive, second quadrant is active. First quadrant is positive, passive, second quadrant is active. Actually, both passive and active is correct option, but this option was not given. Was not given in exam. Was not given in exam. Actually, this option was given. It is correct. Both passive and active you should say, but it was not given. But generalization. What is generalization? Generally, not generally. Passive element can never become active, but active element can also become passive. See the concepts are. Passive element can never become active, but active element can also become passive. Okay, now passive element can never become active, but active element can also become passive. So globally active. Passive element can never become active, but active element can also become passive. Passive element can never become active, but active element can also become passive. It is globally active. Okay, now then understand again. Is any mirror image between 1 and 3 or 2 and 4? If 1 and 3 mirror image, it is passive symmetry, passive bilateral. If 2 and 4 mirror image, it is active symmetry, but it is neither passive nor active. So it is unilateral only. Because no mirror image. So final answer. Yes, final answer is it is non-linear, active, unilateral. That is the answer. Okay. Non-linear, active, unilateral. Okay, na? Chalo. Now I'm giving another example. Everybody should see, actually, this is non-linear because homogeneity failed. Doubts at last only, please. So it is non-linear as homogeneity failed. Like doubling the voltage is not doubling the current. Both passive and active is the correct answer, but that option was not given. But you have to generalize that. Most of the examples, majority again you have to take, not unique simple example. Majority wise, passive elements can never become active, but active elements can become passive generally or more in quantity. So globally active. And there is no mirror image between 1 and 3 or 2 and 4. So it is unilateral. So non-linear, active, unilateral. Now another question. I'm giving another question, everybody. Yes, I'm giving another question, everybody. Okay, now this is the characteristics. Chalo. Yes, everyone should answer this. Everybody should answer this. And I'm giving another gate question for Tribly. This is also I'm giving. So this also you should answer. Both questions are. Everybody answer both questions. I'm giving only 1 minute. Everybody answer both questions. Okay, everybody see. Left side you see, actually, this is linear or non-linear. Again, it is not obeying Ohm's law, sir, because you see, it is non-linear. It is parabolic, na? So it is non-linear. Non-linear. Passive or active? 2 and 4. Active. Active. Non-linear active. But is it mirror image? Yes, 2 and 4 mirror image. So it is bilateral. Bilateral. So it is non-linear, active, bilateral. See, even mirror image in 2 and 4 is active bilateral. Active bilateral. Mirror image in 1 and 3 also passive bilateral. Remember that. Actually, we learned only 1 and 3, but does not mean it is active bilateral. See, 2 and 4 also mirror image is active bilateral. 1 and 3 mirror image is passive bilateral. Okay, now here you see, very interesting. Linear or non-linear? Non-linear. See, the first quadrant it is linear, but in second quadrant it is non-linear. Why? Because voltage is decreasing, current is increasing, sir. Voltage is decreasing, current is increasing. It is non-linear, not just straight line you have to see. Voltage is decreasing, but current is increasing, non-linear. Passive or active? Actually, it is both passive and active. Both passive and active. Yes or no? Both passive and active. But this option was not given in gate. So globally active again, globally active, because I told passive element can never become active, but active element can also become passive. And it is unilateral, bilateral. Now there is no mirror image between 1 and 3 or no mirror image between 2 and 4. No mirror image between 1 and 3 and no mirror image between 2 and 4. So it is unilateral. 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 So answer is non-linear. So I will write here non-linear, active, unilateral. Unilateral. That is the answer. Okay, now? Chalo, we will stop here, sir. And now you can ask doubts. Yes, you can ask doubts. Otherwise, take your time. Tomorrow also. See, tomorrow everyone remember, sir. 7 to, everybody remember. Tomorrow 7 to 8:30 one session, 8:30 to 9 break, and 9 to 10:30 second session. Okay, na? So take your time, sir. We will continue from here. This topic is not over. We will continue from here tomorrow by giving more examples and more clarity. Until then, please wait. Okay, na? Chalo now, Kushal, tell me what is your doubt.
Hello, sir.
Tell me, Kushal.
Sir, in the rechargeable battery, I didn't get how the voltage is positive and current is negative.
No, it is not that meaning. See, actually in a battery, suppose you take a battery like this, plus terminal, minus terminal. See, when you are connecting any load, we are taking what generally most of the applications in the world are sinks or sources, sinks, na?
Yes, sir.
In your house also, sinks are more, but sources are less. That is why we have given that first quadrant for sink notation. That means what I will take, if current is leaving the positive terminal of battery, then I will say it is a source, but that I will take it in the negative quadrant. So from battery point of view, current leaving positive terminal is a source concept.
Okay, sir.
But because in the world generally most of them are sinks, so that is why I allotted in the notation what I did, I allotted first and third for sinks and second and fourth for source. That is only a notation, our understanding this is. Now with respect to that battery point of view, here current is leaving positive, now it is source mode. Source mode means this mode.
Yes, sir.
But suppose battery charger is there. Now the same battery you plug it to charger, like your battery charger, okay? Then from that AC terminal, it will rectify and make it DC, and that will drive the current inside the battery.
Okay.
So current has reversed, na?
Yes, sir.
That is why reverse direction I'm showing.
Okay.
But I have allotted first quadrant as sink.
Yes, sir.
Understood?
Yes, sir. So second and fourth quadrant for source. Yes, sir.
That is our notation. That is only to understand. Actually, who is giving these quadrants? Our engineers only are giving. Our engineers only are giving these quadrants actually. That is to understand properly. That's it. Mathematically, we are understanding. Okay, na?
Okay, sir. Okay.
Okay, right. Okay, so everybody, don't see, this is introduction class, sir. Don't worry. Tomorrow, very cool, very slow, very neatly will go, but it will take time. See, I told you, sir, first 8 hours you leave, sir, because this will be like this. All basics, definition, formula, notations. It looks like that first few classes, because if I don't give these definitions, actually some students may not understand. But at the same time, definition level is not great, sir. We should go high level. But that is why first 6 to 8 hours it will be like this. Don't get irritated. But once these definitions are over, now, sir, then very neatly with lot of practical examples I will go. Okay, na? So tomorrow 7 o'clock, everybody, please come. And tomorrow 7 o'clock to 8:30 first session, 9 to 10:30 second session. Okay, na? Mahesh, what is your doubt?
Hello, sir.
Tell me, Mahesh.
Sir, once confirm, sir, whether it is for all or for only BTech computer batches.
Sir, that thing I cannot tell, sir. I don't know. Schedule manager is giving. I don't know all this, na, sir. See, for me, which student is what? I don't know anything. I don't know your background. I keep teaching whatever is necessary, sir. I don't know. Really, I don't know, sir. But you put a mail to our schedule manager. You ask them who is there here, who is not there here. I really don't know, sir. But what is your problem? You tell me.
No, we are college goers, so we will.
So what is your, no, you tell me what is your problem. I will intimate to him. What is your problem?
Sir, we cannot listen to some morning section.
Morning. See, okay, 6 to 9 is okay.
No, sir. We are going to college at 8 o'clock. How can we listen, sir?
I will ask them. Chalo, tomorrow you remind me again. Mahesh, what you do? Tomorrow morning you put a message in question and answer. But today what I will do is I will ask him, is college goers combined here or what are their timings? Is there any possibility for change? I will ask. Okay, na?
Okay, sir.
I will ask because I don't know all this here because we don't know whether it is a PM batch or long-term batch or Spark batch or GM. We don't know. Generally, what happens, na, sir, in the last time, this now is already October, na, sir. Already all batches combined network we don't complete now. Then remaining subjects will not complete even by January. Understood, na?
Okay.
I will find out. But I cannot guarantee anything. I will ask him and tell you by tomorrow. Okay?
Okay.
Okay, right. So tomorrow, everybody, 7 o'clock.